First session will be on laser output controls. So we discussed different type of lasers, solid state lasers, gas lasers, and even dye lasers. We found some of laser they are giving a constant output or different frequencies, and some of the laser they are giving the tunable output, and we can use these lasers for different applications, and different application there is a different type of requirements. So as a result we can tune, or we can also play with the output of the laser optical elements, or using some techniques, so that a device can be utilized for many applications, so that its versatility can be enhanced. So second session will be on the semiconductor lasers. I mentioned they are also part of solid state lasers, but here pumping mechanism is different. These lasers they are specifically called injection laser diodes, or even diode lasers. They are specifically designed for these optical communication, because in optical communication we know the fibers are very tiny fiber. They are the core diameter is of the order of 10 micron for single mode fiber, or it is 50 micron for multi-mode fiber. So as a result we need very small device, so that there is a compatibility between your source and optical fiber. So we should be able to couple our source with the optical fiber. In that case we need a very small device. So and second part is the modulation part. So which I should be able to modulate my source. So these type of devices they are based on the input current, injection current. So injection current can be modulated like any other device. So and then there will be optical fiber communication. So Professor J.K. Sabda, who is ex scientist from CSIO and presently professor at Jeend Institute of Engineering and Technology, Haryana. So he is a fiber optics expert. So he will engage this session. So and in the afternoon we will also go to our laser and fiber optics laboratory. So there we will perform some experiments based on the semiconductor lasers from 2:30 to 3:30. Then from 3:30 onward there will be a lecture by expert from MT University of Engineering and Technology, Professor Devara. He is an expert in the area of laser technology and optoelectronics. So he will take a session on laser based standoff detection of explosive materials. So this session will be from 3:30 to 4:30, or maybe it may go up to 5:30, depending upon the how much time the speaker take for this session. So this is the schedule of today. So then, so with this I will move to my presentation. ये कहाँ गए? अभिजीत को देखना. Okay, मिल गया. Yes. So I will start with the session. So this is on techniques to control laser outputs. So we know different type of lasers. Some lasers are 3-level laser, some lasers are 4-level laser. We have the solid state laser, we have the gas laser, we have the dye lasers, then we have the semiconductor lasers. So some lasers they give the continuous output, some lasers they give the pulsed output, and even we will find they are the multi-frequency lasers, or they are the multi-mode lasers. Number of modes are there, number of frequencies are there, and for different applications we need a specific characteristics of light for particular application. In some cases we are more interested in the monochromaticity. In some applications we are more interested in the intensity of the output. Maybe some other application we are more interested in the divergence of the beam or the polarization of the beam. All these parameters are important, and our source or laser is application dependent. So which characteristics is more important for a particular application? So laser beam is controlled according to that purpose. So we will, this is a content outline I will cover. So need to control beam outputs, then selecting single frequency. In some application we need single frequency or single wavelength. For example, for single mode communication, single mode optical fiber communication, I need a single mode, and for propagation we know the optical frequency. Present rate they are working on either 1310 nanometer or the third window is 1550 nanometer. We want these wavelengths to be as narrow as possible. The spectral width of the source should be as small as possible. Lambda plus minus delta lambda. So 1310 plus minus. Smaller it is, more will be the data rate. It accounts for what is called the broadening of the pulse. So we need single frequency or single wavelength. So similarly, for single mode propagation, we need the single mode. Selecting the single mode. So when we discussed these cavity, laser cavity configuration or cavity conditions, and then we find there are the longitudinal modes and there are the transverse modes. All the longitudinal modes, they contribute to a fine spot, a point spot. And in communication or for any application, we are interested in power, where the power falls. So if you get a very, very fine spot, all the power is concentrated at one point, and for a detector, it is easier to measure. And even for a source to fiber coupling, it is easier if your source is a fine spot. But transverse modes are not the spots. As you go to higher and higher transverse mode, they spread up. So as a result, we are more concerned with the fundamental transverse mode, what is called TEM00 mode. So TEM mode is the important for the single mode fiber. So controlling of transverse mode is very, very important. So we will go for that also. Then for some application I need high power, like in the material processing or in the medical field, like cutting or crushing of some stones. So high power, high intense pulses are required. So in that case we will go, we will also discuss that techniques to generate the high power pulses. Similarly, these are the different techniques: Q-switched and mod-locked lasers. They are the laser which give us the high power outputs. So we will discuss these in detail in the coming part. So these are the different applications I mentioned in the first session. During the overview of laser technology, you find different applications. You find lasers in research. Different type of spectroscopy, different type of laser-based techniques are there. So they are extensively used in different type of scientific research or any industrial application. Then in the medical field, I mentioned they are extensively or widely used in the optical surgery or department of ophthalmology or eye surgeries. Then in general surgeries for all type of cutting and other medical applications or other surgeon applications. Then for different type of diagnostic techniques or therapeutic techniques, we use the lasers. Then in entertainment industry, now we have all CD player, DVD player, video games, all type of these they use the lasers. A laser is used as a you can say pin to write and to read a disk. Similarly, in telecommunication, I mentioned this information technology. It is only possible because of the optical fiber communication. We are able to communicate, we are able to connect with number of centers through ICT. It is only because we have the bandwidth of the communication industry. It provides me the connectivity. Otherwise, it was not possible. So information technology is only possible because of the communication. Without the communication industry, information technology cannot boost. So then we have the, in fact, telecommunication, even the satellite communications also. Satellite to satellite, one communicate through laser, free space optics. So that is another area. Then holography, holograms. Dr. Rajkumar, he discussed in detail yesterday different type of holograms. So many features are there, and holography now itself is a technique. and this technique only worked with the laser. In fact, holography and your optical fiber communication, these were the two areas which were waiting for the laser to come or optical source to develop or coherent optical source. Then in military application, I mentioned lasers. They are used as a for the radar purpose or as a weapon purpose or as a guiding purpose. So all these are the different applications. Then industry, so many applications. You name any industry, it may be a mechanical industry, it may be electronic industry, any chemical industry, or your nuclear power and technology. So many, any industry you will find laser in use directly or indirectly. So all these wide range of applications are there. Their lasers are used. As you see, all these applications, the requirements are different. In medical, requirements are different. In communication, requirements are different. In holography, requirements are different. So different requirements are there. So we need number of lasers in the whole range of spectrum, starting from IR to UV region, in all the optical region, and with different characteristics. So we discussed in laser the block diagram of a laser. We discussed that there is a active medium. It may be solid, liquid, gas, or semiconductor. Then I need a pumping source. It may be optical pumping, it may be electrical pumping, or it may be a direct conversion, like in case of the semiconductor lasers. Then we have to create, in order to get the more amplification or large stimulated emission, we need two mirrors to create a resonator, to convert a ordinary configuration into a optical resonator. So one mirror is, this is a fully reflective, and one mirror is partially reflected, maybe around 90 to 95% reflectivity. So we get from 5 to 10% power at the output. So here come the other elements. These other elements are basically optical devices used to control or tune the laser output. So these are mostly the optical component, maybe the prisms or diffraction gratings, or some type of the maybe electro-optical or magneto-optical or acousto-optic elements. So these elements are basically to control the laser. So today we will concentrate on these other elements. So optical devices. So control of laser output is required. See, many applications of lasers are there, and all different practical applications, they need modification or control of the beam. The modification may be in terms of the, mostly in general, it is in terms of the frequency characteristics or mode characteristics, and then power output. So these are the two parameters which are very, very important for different type of application. Mostly with these characteristics, they fulfill our requirements. So usually carried out using the optical accessories or optical elements. So laser beams are modified either inside the resonant cavity by affecting the process of laser oscillation. So in that case, even laser mechanism is affected, or outside the cavity by passing through a device with variable transmission. So you allow the beam to pass through a element which will change the characteristics of device. Like I think on Dr. Rajkumar, he discussed about parametric oscillations or different type of amplifier. If you have a laser output, you pass this output through a amplifier, so it will be amplified. So similarly, you can pass the laser output through a different type of saturated absorbers are there. So those absorbers, they will become transparent or they become opaque depending upon the intensity of light. So they are outside that. So it means your cavity is not affected. So in many cases, it is preferred that your laser mechanism should not be affected. So it is sometimes better to put the element outside. But all things cannot be fulfilled if it is outside. Sometimes we have to put something within the cavity also. So these are the way. So we use the optical devices. Mostly we come across two type of devices. One is the passive devices. So what is the role? What are the passive devices? Mostly we have the prisms and gratings. They are the passive element, and we have the passive element, we have the active element. What is the difference in two? Passive and active devices. Okay, active? Not in that sense. Anyhow, so passive devices, they do same thing always. For example, your resistance, it will always offer the resistance. Your prism, if light fall on the prism, it will disperse it. If light fall on the grating, it will diffract it. On the other hand, we have the amplifiers or other devices. So depending upon the input, amplifier will give you the different output. It will be saturated also, it may not be operational also, depending upon the input. So we have the active element, we do different things at different times. So depending upon the light input. So prisms or gratings, passive devices, they are employed for selecting narrow range of frequencies. So our requirement is to get a fine frequency, a tuned frequency. So to tune a laser to operate at different specific frequencies or at different modes. Then active devices, they may be rotating mirrors. So we use mirrors in the cavity. The mirrors may be fixed mirror or it may be rotating mirrors. If it is a fixed mirror, it will give you the feedback. If you rotate this mirror, you will not get the feedback. So it depends upon the position. Whereas in case of prism, you put it in any form, it will disperse. Or optical modulators. So optical modulator, they will modulate the light. So again, depending upon the conditions. So they are mostly employed to concentrate light energy into short time intervals or pulses. So to convert the continuous wave power or continuous wave into a pulse form. So when it is in the pulse form, you get large power. In the pulse, you get the energy. So it is a basically optical energy. Your output is a optical energy. So you find the rate of this energy, you will get the power. So pulse over the time duration, that will decide how much is the power. So depending upon the duration, if it is a millisecond pulse, you will get kilowatt of power. If it is a microsecond pulse, you will get megawatt of power. If it is a nanosecond pulse, you will get gigawatt of power. It may be picosecond or it may be femtosecond also. So you may get very, very high power. It is possible now with the lasers. But you have to use some technique. So the first part, selecting narrow frequency range. So we discussed in the laser and in the laser cavity, number of frequencies are there under the gain profile. I hope you remember, we discussed optical resonator, number of frequencies are possible of different wavelength. Your length of the cavity is integral multiple of lambda. 2 mu L equal to m lambda. Number of wavelengths or number of frequencies are possible. Then there is a gain profile of the medium. So we find the product of gain profile and frequency output, and those frequencies which fall under the gain profile, they will be excited or amplified, other will be suppressed. So still there are number of frequencies. So if you have a set of frequencies, then some laser emits, so desirable frequency can be selected. So in that case, if you have a set of frequencies, the set may be maybe 2, maybe 4, maybe 5, not very large. Set is always a defined value. So in that case, the simple case is like in helium neon laser. If you remember, in the helium neon laser, the most favored transitions are, this is 3.39 micron, IR region, 1.15 micron and 0.63 micron. So these are the IR wavelengths, this is a visible wavelength. There are other transitions, but those transitions are very, very big. So by selecting the feedback, they can be they can be suppressed. So but these three are the intense transitions. So for many applications, you will see that if you need a red color from the helium neon laser, in many cases it is a red color. So as a result, I can put coating over the mirror where IR frequencies or IR wavelengths are absorbed. So the mirror will, in the feedback form, the mirror will only reflect the visible rays. So only this 0.63 micron will be reflected back, others they will be absorbed. So they will be not included in the amplification process. So as a result, we will get the single 632 nanometer wavelength from the laser. So in this case, we can, the simple method of obtaining is desired frequency is by suppressing the other frequencies. You have to choose some means so that other frequencies can be suppressed. Only one should travel. Like if Professor Savla, he will discuss, in optical communication we use special type of lasers for communication. We call it as the DFB laser, distributed feedback lasers. So there we use the Bragg gratings. Bragg gratings are very fine gratings, which will, the feedback is very fine. So in that case, we get the laser with the separation with the spectral bit maybe of the order of 0.001 nanometer. Normal Fabry Perot lasers, your line spacing may be of the order of 1 nanometer or 0.5 nanometer. But with those type of feedbacks, it can be 0.001 nanometer or 0.01 nanometer is very common. So with a special effort, so it depends how, what is your feedback, how narrow is your feedback. So it is achieved by coating the reflected mirror of resonant cavity by highly refractive material at desired frequency and absorptive at the other frequency. So others have to be absorbed and desired frequency has to be reflected. That is available for amplification. And through all these cycles, desired frequency will be amplified more and more, other frequencies will be suppressed. So desired frequency is sustained and amplified, other frequencies are strongly attenuated. But so in case of helium neon laser, mirror are coated with material having high reflectivity at 632 nanometer and lower reflectivity at IR wavelength. So different type of oxides they are put over the mirror. Magnesium oxide or some other type of oxide, depending upon the wavelength, they can be the mirror can be coated with those type of oxides and specific frequency can be selected. But if there are large number of wavelengths, it is difficult to putting more and more coatings. You can put few number of coatings. If you go on adding, so that will not be effective. So if you have a set of frequencies, then you can put coating over the mirrors. Now if there are the large number of frequencies, if you have a wide frequencies, not a set of frequencies, so then coating will not serve the purpose. Because the coating, they will also, one type of coating may affect the other also. So it is a layer by layer you have to create. So net effect may not be there. So if you have a wide range of frequency, in some lasers, there are the broad emission lines. So in those cases, we use the passive element like prisms or gratings. So in that case, the light fall on the prism or grating, we know that a prism. The prism always disperses the incident light beam into component of different frequency. Dispersion phenomena is because of prism. So a beam will fall on the prism, it will be separated into different wavelengths. So we can tune specific wavelength. I will show in the next diagram. You can put there is a prism, one can put the mirror. So which wavelength is to be retraced? It has to retrace the path depending on the angle of the mirror. You can tune the mirror and you can choose any of the wavelengths. So for getting the set of for given setting of the prism, only one of the frequency retraces its path into the cavity. Others will be centered out. So only one frequency will be amplified, other will be suppressed. So similarly, in case of grating, we know the grating elements. Yesterday we saw in the lab. So a grating element it separates the different parts. So you can put your element or select your element accordingly. So it follows the 2d sine theta equals n lambda. So this is the diffraction. So only at particular value of theta, only specific wavelength will be reflected. So this is how you will see here is fine. So you have a outward mirror, you have a laser. Particular vector is for the dye laser. It can be any laser output. Now this output fall on the prism and then it disperses. Now this is the tuning mirror. This beam, how it is not, no, it is a set of frequencies. If you have a set, we are choosing one frequency out of wide range of frequencies. So it cannot be monochromatic. So by tuning this mirror, I can select of the frequency. The wavelength or frequency which will retrace, that will depend upon this angle. So particular wavelength will be reflected back and it will be amplified in this process. Similarly, we have the grating. So grating, when the fall on the grating, so grating it will reflect only one frequency. If the beam is falling at different angle, only one beam, one frequency will be retraced, others they will go out. So again, by tuning of this grating, by selecting a angle of this grating, specific frequency can be tuned. So in most of the cases, the laser can be tuned to different frequency within the laser emission line by rotating the grating. So one have to put these elements within the cavity. These elements has to be put within the cavity, not on the mirror. If in the first case, coating is over the mirror. So your laser process is not mechanism, medium is not affected. But here it is within the medium. So, but if you see in both the cases, mostly one prefer the gratings because prisms are the triangular components, and your tube or device is a circular device. So sometimes it is difficult to adjust the triangular component, whereas the grating is a flat. So mostly gratings are preferred over the prism. So these are the two ways. If you have a set of frequencies, you can put coating over one of the mirrors. If you have a wide range of frequencies, we have to use some passive devices. And by tuning those devices, tuning the given setup, one can select the desired frequency. Okay, so single frequency is available by these methods. So then we need single mode also. For a single mode optical fiber communication, I need a single mode. Single mode optical fiber, they operate with a single mode source. Multi-mode fiber, multi-mode source works. So you need a optical source or laser which has a single mode operation. So out of large number of modes, transverse modes, it is often desired to select the fundamental mode, TEM00 mode, because this mode is a very fine spot. Other modes, they are broadened. So if such type of power fall on that is coupled to the optical fiber, it will not travel in the optical fiber. Your coupling will be very coupling of power will be very less. So large amount of power will be lost even at the source to fiber coupling. So we need a very narrow source with a very narrow or fine mode. It can be selected by keeping the circular aperture in the cavity. Normally, if large amount of light is falling in, say for example in this room, I can put a very small aperture so that small amount should come. So you can control by putting the aperture. But in this case, if you put the aperture, what will happen? Your power will also reduce. This is one way. If more power is not required, you have a large amount of power, you put a small aperture, only small power will transfer. So, but it is not always desired. You are getting the you can say lower order mode at the cost of power. On the other hand, we can use unstable optical resonator, parallel or confocal telescopic resonators. They also give you very fundamental mode. But on the other hand, this is the unstable oscillator. If there is a any small angle tilt in the mirror, beam will go out. So like your parallel configuration cavity, parallel mirror cavity. So that's why we prefer the curved mirror cavity. In that case, the small tilt will not affect the system. So it is also possible using the confocal telescopic resonator, but again it will be a unstable oscillator. So a line, it should be exactly at 90 perpendicular direction. Small angle will make the difference. So as a result, we can use one of these methods or these applications. So, but even if you choose any these fundamental modes by using any of the methods, so then even you will see, even if laser oscillate in its fundamental transverse mode, there exists a large number of longitudinal modes. Large number of modes are there, longitudinal mode. So when these modes they travel, there are always disturbances. They may change their position. So that lead to broadening. So as a result, we prefer there should be single transverse mode and single longitudinal mode. And those modes are associated with the frequency. They are associated with the number of frequencies. Number of frequencies, number of modes. So the simple method of obtaining single longitudinal mode is by reducing length of the cavity. I hope you remember when we discussed about the cavity, resonance cavity, we find that the frequency mu is given by some C over 2 mu L. L is the length of the cavity. So separation between the mode is C over 2 mu L. So by reducing the length of the cavity, I can increase the separation. By increasing the length of the cavity, I can reduce the separation. Okay. So separation between different modes can be affected by changing the length of the cavity. And now the gain profile. Gain profile is the property of the medium, of the material. Gain profile is same, but the frequencies are now broadened. So instead of large number of frequencies falling under the gain profile, you will see only 1 or 2 frequencies will fall under the gain profile. Others they can be separated out. So you will see here. So in this method, we use what is called the Fabry-Perot echelon. Single mode axial oscillations may be achieved without reducing the cavity length. If you reduce the cavity length, that is the one approach. But if you reduce the length, what will happen? The material contained in this will be lesser. Volume of the material which will be there, that will be less. It will not be able to contain large, more active medium. The medium will be, the quantity of medium will be less. So lesser the medium material, lesser will be the power again. Because it depends the atomic density. Material per unit volume. Length is less, small, volume will be small. So in that case, it is also at the cost of power. So we use some elements, which are the optical element. One is called the Fabry-Perot echelon. It is similar to Fabry-Perot cavity, but it's very small in length. So basically, in this case, we have a laser cavity, then we have a Fabry-Perot echelon. It is called Fabry-Perot echelon. It's a very narrow. Its length is very small. So basically, we have two oscillators in the resonance with each other. One is the major laser cavity, other is the Fabry-Perot echelon. So they are basically optical elements like this, which are polished from both the sides. So it forms a cavity itself. So only one mode will be sustained. You will see how it works. So this is how it does. Fabry-Perot echelon will work. You have a laser medium, same laser tube, you have the mirrors, and you put this fabric echelon here. You see, the length will come into like this direction. This is the length of the cavity. It is placed in such a manner that when the photon they will travel this length. So this is the gain profile of the medium, of the laser medium. Now these are the frequencies which are coming out from here. Okay, large number of frequencies. Now when these frequencies they pass through this Fabry period echelon, the oscillation conditions, resonance conditions for this cavity, now they will follow this pattern. Now L is small. This is from this L. This is from L1. So now in this case, C over 2 mu 1 L1. These are the parameters of this cavity. Now L1 is very, very small. So now this separation, the separation with this mode will become this much. Similarly, separation of this mode will become this much. So you are increasing the separation between the different frequencies, and now the net product output will be product of gain profile and net output. Now in this case, only one frequency fall under this gain profile. These will be suppressed. They will not be amplified. So it is by controlling by putting one element within the cavity. So you will get sufficient power also, and only few or single frequency. So these Fabry period echelons are used to get the single axial move. These are your axial frequency or axial frequency. Axial frequency or axial move. So transverse mode can be selected by reducing diameter of the tube. Just like in optical fiber, we go from multimode fiber to single mode fiber. Multimode fiber, the diameter is 50 micron. Single mode fiber, the diameter is 8 to 10 micron. So we reduce the aperture. Similarly, the tubes are kept very, very narrow if we are selecting the single transverse mode. In most of the laser, you saw yesterday in the helium neon laser, the tubes are very narrow, maybe few centimeters in diameter. So Fabry period is the one way to get the single mode. So these are the different techniques. So we can select the single frequency, or we can select the single mode by using Fabry period echelon or prisms or gratings, if you have a wide range of frequency or wide range of modes. Okay. So any doubt or any query to the frequency level? So then we will move to the second requirement, is the pulses. So we need high power. In many cases we need the high power. In optical communication, power is not the requirement. High power is a problem there. We know there are non-linear effects in the optical fiber. So power requirements are only of the order of milliwatt, few milliwatt. Even 5 or 10 milliwatt is a large power in optical communication. So whereas for many other applications like industrial application or in holography, you need large power. So some of the laser works in the CW mode, continuous mode, while other operate in the pulse mode. When you are talking about the continuous wave mode, the power is always less. Whereas in the pulsed mode, the power is more. In both the cases, power obtained in general is not as per industrial requirement. The pulses are, it depends upon the lifetime of the level. The pulses are not very, very narrow. They are broad pulses. So broad pulses means time duration is large. So lesser power. So for many applications we need large power, and there are different techniques. How to get large power? How to get what you call as the giant pulses? So different techniques are there. One is called the Q switching. Here we talk about the oscillator, and when there is an oscillator, we call it as the quality factor. So what is the quality factor? It is energy stored in the oscillator over losses in the oscillator. So energy stored over losses. If losses are less, Q is more. So high quality. If losses are more, Q is less. So low quality. So define it is related to quality. High quality and poor quality. You know the difference. So we have the Q switching. Then another method is cavity dumping. It is another technique where we dump all the power at one instant. They are just like dumpers. In civil work or in construction work, they use the dumper to carry large soil or other type of material. And then they have the arrangement, they dump it at one time. So same is the cavity dumping. Your cavity is full. It is totally loaded. And you make some arrangement and to take out all the power. Again, that arrangement can be taken out, and again the pumps will work. They will take the cavity to peak value, then again it can be taken out. So dumping is also another part. One is the mode locking. Third technique is the mode locking. Mode means we know that most of the laser they work in the multi modes or number of frequencies. So if these modes they can be locked, they can be phase matched. If they are in phase, the amplitude they will add up, you will get large power. So these three techniques are used: Q switching, cavity dumping, and mode locking. So out of these, Q switching and mode locking, they are most favored and most preferred for different laser getting high power outputs. They enable to produce large power during a short interval of time of the order of nanoseconds. So mostly when we talk about the high power, these are the pulsed power. So pulses are converted. So continuous power will not be very, very high. If you want to get it at the continuous mode, when it is high power, it will produce lot of heat, lot of thermal heat has to be compensated. You need very, very powerful heat sinks or very, very active cooling. But when it is in the pulsed form, a pulse comes, then there is a duration for the second pulse to come. In between, the material will be relaxed. The thermal heat will be dispersed in the material. So that type of hard cooling is not required. So that is the benefit of pulses. So quality factor, I already mentioned the Q. It is a quality factor which is important here. So the Q switching is based on this quality factor. So if we take the example, normally the quality factor in electronic oscillators, it is of order of 100, whereas in case of lasers, Q is very, very high, of the order of 10 to the power 7 to 8. So very high Q factor means loss is very, very small. We have to control the loss. So it means by controlling the loss in the cavity, we know that in the cavity there are losses and there is a gain. The amplification is always a race between gain and the loss, a balance between loss and the gain. And lesser the loss, better is the output. We know, we discussed the optimum output power. It is all the losses which are there. So threshold level. Lesser the losses, lower will be the threshold level. So it is related to that part. So in the laser, we know the laser threshold. The relationship between laser threshold and quality factor. So alpha 0, this is the, let it be the lasing threshold. And this is the wavelength and this is the quality factor. So lasing threshold can be related to quality factor. So it is inversely proportional to quality. So higher the quality, lower will be the threshold. So when the laser is at high Q, it is easier to achieve the laser action. Threshold will be low, so laser will give the output. When the Q is high, threshold is low. When the Q is low, threshold is high. So in that case, it is difficult to get the population inversion and laser action. So when Q is high, laser will operate. When Q is low, laser will not operate. So we can control it, we can look it. The threshold condition depend upon the reciprocal of quality factor. Higher the Q, lower the threshold, so laser will operate very easy. And lower the Q, high threshold, difficult to achieve. So we will discuss the Q switching of for giant pulses, the Q switching part. So we know the power of a laser can be drastically increased. We will get a high power, low power, it depends upon population inversion. Larger the number of atoms in the upper laser level or larger is the population inversion density, more will be the output. Okay, so it means large number of atoms in the active medium participate in the stimulated emission. So only happens when population inversion density is very, very high. So we know normally when laser operates, oscillate, the population inversion comes back to lower value. More output means large stimulated emission, and when there is large stimulated emission, large number of atoms come to the ground state. So population inversion decreases. The gain increases or output increases, population inversion decreases. There is a balance between two. So therefore it is necessary that if you delay the onset of oscillation, so if the trigger is not available, the stimulated emission will not take place. Onset of oscillation can be delayed. On the other hand, pumps are working. So more and more atoms are being pumped to the upper laser level. Photons, trigger photons are not available. So stimulated emission will not take place. And once the trigger photon is available, stimulated emission starts and there is an avalanche of photons. You will get large. So this is the mechanism used here. So laser can be prevented from oscillation if parallelism of the resonant mirror is disturbed. In order to get large stimulated emission, you need large energy density, large photon density. Now, if your mirror is not reflecting the photons will energy density will be less. So if the parallelism of the mirror is disturbed, the feedback will not be there. So this is how the parallelism of resonant mirror can be disturbed. So if one end of the mirror is misaligned, it will not reflect the incident photon into the active medium. Okay, so therefore stimulated emission cannot take place. So photons are not, there is not large energy density of the photons. So the photons will not be available for the, so lesser number of photons are. So feedback will not come back. So whatever feedback is there, so the photon is coming, it is not coming back, means it is a loss. It is a loss. So if it means loss increases. So increase in loss means Q will increase. So okay. Consequently, let me see. In this effect, the pumping process can build up the population burden to very. So okay. Now when one of the mirror is there, now is misaligned, the photons are now there is no feedback. Pump is working, so the population burden will increase. Now to bring the mirror. Parallel, so feedback will come, so stimulator will take place. This is what I have already mentioned. So Q factor of resonance is spoiled and optical loss are increased to very high value. So when there is no feedback, so laser will not operate. When there is no feedback, laser will not operate. So in that case, your Q factor will be spoiled. Q factor will be very low because loss are more. So as a result, we will see in this slide. If now the one of the mirror is aligned, it reflects the photon into a laser beam and you will get the feedback and there is an avalanche of photons. So when there are the photons available, all the energy stored in the cavity will be emitted in a single large pulse. So this is the one way. So when the mirror is aligned, you will get the feedback. When the mirror is not aligned, there is no feedback. So as a result, there is no feedback. So as a result, large population inversion is there. Further, if you bring the mirror parallel, feedback is there, so population inversion will take place. So by affecting the mirror, the pulse lasts for a short time and depopulate the upper level. So when large number of photons or atoms come down, the population inversion condition will decrease. So more number of atoms will be at the ground state. All the atoms from upper state, they will come down. So N3 minus N2 will be negative. So laser will not work. So let us see how. So this method is called the Q switching. So Q switching can be obtained by this method. See, for example, initially what will happen? Your pump is working and your mirror is not aligned. Mirror is not, the photons are going, they are not coming there. So means there is a large loss in the medium. So you have a large loss. At the starting, you have a large loss. Okay. Now your pump is working. The gain is increasing. You are pumping, and more atoms are taken to the higher level. So gain is increasing. It goes up to this level. When it is near to the loss, now you align the mirror. Now the photon, they will come and we get the stimulated in this task. So when the mirror is brought down, the photon will come back. So loss is decreased. So in this case, the loss is decreased and the gain now crosses the, in this case, the loss is this one. The gain is here. The difference of 2, it will give you a pulse. How large this difference is, the stronger will be the pulse. So when the gain, this is the gain, this is the loss, this is the gain, when they balance each other, this is the threshold condition. The laser will oscillate after the threshold. So you will start getting the pulse here. When it is here, it will start oscillating, then the difference, and then ultimately again, this is the maximum value, saturation level. Now when large number of photons, atoms come down, again it will finish. So population inversion will be, there is an avalanche of the pulse. So we will see by operating the laser in the Q switched mode, the energy of the laser can be concentrated into a single pulse. So it depends how fast rotation it is. This is the one approach. So simple part, initially when you start the part, the mirrors are not aligned, it will take all the atoms, large number of atoms to the higher state. Now you bring the mirror, atoms are already in the very, very high state, the photons will come and all they will come down. This is just like when a blacksmith, he always make a stroke when iron is red hot. तभी आपका जो भी है tool बनेगा. You can crash the iron in that case. So in that case, your medium is in a very, very energetic position, very, very hot, but it need a strike. So you strike, you make the mirror parallel, then the photon come and all the atoms, they will, because stimulated emission once started, it multiplies. So you will get the large pulse. So the pulse duration depends upon the factor how fast the mirror is rotated. It depends upon that part. So Q switching is very widely used, but not in all the cases. Mirror rotation is not always possible. So it is this case when the peak power is very, very high. So in that initial case, you see this is the loss and you are increasing the photon density and you will get, this is the peak power. So this is your, you see this is your threshold level and you will get the peak from here. The loss will fall from this level to this level and this is the population density. The photon, they will increase and then you will get the pulse of this time duration. So it depends upon peak power is your N0 h nu over 2 Tc. So how large is N0? So this is your population inversion. It is very, very large. and once the photons is available, it will come down, and now it is very, very small. So you will get pulse duration only from this period to this period. Here the laser will stop working. So this is your photon density. When the mirror is misaligned, no photon feedback is there. When the mirror is aligned, the feedback will increase. In one shot, few photons. Second round, more photons. It will goes on increasing, and then these photons they will come as an output. Because output increases, the number will also decrease. So you get the pulses. This is the one pulse. Then again the mirror is misaligned. The pumps. Then it will be aligned. You will get the second pulse and other pulse. So in this way, if you find the average power is here. This is the average power of the laser. This is the Q switched peak power, Q switched power. So you will get large pulses. Average energy is always less, but here in the pulse, the energy is more, peak energy. So all this part is, so peak power Q switch laser can be many times larger. Power will be many times larger than the continuous power, and it depends upon NGO or TC. Smaller the TC, more will be the peak power. So how many number of atoms are participating, and what is the duration of the pulse? TC is the duration of this pulse. So it means your tuning of the mirror has to be very, very fast. At what rate you can rotate it? It may be millisecond, it may be microsecond, it may be nanosecond or more. The pulse duration will depend on the tunability. So there are two important conditions also in that case. Why we are not able to get all the lasers? In all the lasers, by Q switching is not possible. If the rate of pumping must be faster than the spontaneous decay. Now when the atoms are going to higher level, there is spontaneous decay also. If the spontaneous decay is more than the pumping rate, it cannot be populated. So the pumping rate has to be larger than the spontaneous decay probability, and this will again the condition. So otherwise upper laser level will be depleted faster than it can be populated. And below this decay probability, it is inversely proportional to lifetime of the sphere. Okay, so one have to look for this condition. Then Q switch must operate rapidly. So compared to build-up rate of the oscillation. If this condition is not met, we will obtain a wider pulse, long pulse. So TC will be large and peak value will be less. So two conditions: pumping rate should be very, very fast than the spontaneous decay coefficient, decay probability, and the Q switch must operate rapidly. Then only we will get the desired power. We can take the simple case of method of Q switching. So Q switch can be obtained in many ways. One I mentioned is the rotating mirror. Other is we discussed in the lab, electro-optic shutters. So electro-optic shutters, they also change the polarization of the light. So if in the laser you use the polarizer, and if the light axis of light is not matching with the polarizer, there will be no feedback. They will not travel through the polarizer. So electro-optic shutter, then even acousto-optic shutters. Acousto-optic shutter, they are based on the gratings, acoustic waves. When the acoustic waves interact with the quartz crystal, they form a grating. So when switch is on, grating is there. When switch is off, grating is not there. So we will see. Then there are saturated absorbers. So these absorbers, they work when the light is when the light intensity is poor, it is opaque. When the light intensity is high, it is transparent. They are put between laser cavity and a mirror. So if it is opaque, the photons they will not come back, because photons will be reflected from mirror. But when it is transparent, When the intensity is high, it is transparent, it will cross, it will go to the mirror, then it will come back. In that case, feedback is there. So saturable absorber, they also serve this purpose. So we will see in detail rotating mirror method. This is a simple, I mentioned, first method is the rotating Q switching is the rotating mirror. So we have a laser cavity, laser rod, we have a mirror, this is the rotating mirror. So this mirror is rotating. So in that case, when the mirror is parallel, there is a feedback. When it is off, there is no feedback. So when the mirror is not parallel, photons go, they will not come back. So cavity loss is very, very high. So high cavity loss is your Q value is very, very low. So low Q value means high threshold. Okay. So when the mirror is parallel, the photon will come back. The cavity loss is low. So Q is high. So threshold is low. So in that case, the laser will oscillate. So when the mirror is parallel, laser will oscillate. When it is not parallel, laser output will not be there. So how fast you bring this mirror, that will decide the duration of the pulse. So mirror, rotation of mirror, what will be the mechanism? You will use some mechanical device. So in that case, it depends how much speed you can, how much rotation you can achieve. Mostly this rotating mirror method is used in the ruby laser. In ruby laser, it is only because the lifetime of upper laser level is 3 milliseconds. The ruby laser, it has the longest lifetime of the metaspace. Other materials, the lifetime is of the order of microsecond or nanosecond. Whereas in ruby, that's why we can get high power from the ruby. Even of the order of watt or kilowatt. So because 3 milliseconds is the lifetime of metastable state, the atoms can stay there for longer time, longer duration. If it is a microsecond, they can stay there for microsecond. But here they can stay there for milliseconds. So mirror will, so it means the first condition, within 3 milliseconds, they can maximum time of stay is 3 milliseconds. If the photons will not come within 3 milliseconds, they will come down. They will not be available. Stimulated emission will not take place. So within 3 milliseconds, the trigger should stop. So the mirror should be brought to parallel position within 3 milliseconds. So if you look for this part, so if you calculate the speed of rotation of the mirror, it comes around to be around 20,000 RPM. So mirror should rotate at a speed of 20,000 RPM, which is a very, very high speed. I hope everybody is driving the car. You have a RPM meter. At what value it is? Generally, when you are say moving at a speed of 60 km per hour, you must have seen जब एक्सेलरेटर दबाते हैं जोर से आवाज आती है, आज का RPM मीटर लगे होते हैं. Generally, it is around maybe 2,000 or 3,000, not more than that. Because mechanically, it is very, very difficult to get a speed of larger speed. So 3,000, 4,000 is general in the mechanical process, is the rotation you can get. But here you need, because lifetime you cannot change, you need a speed of 20,000 RPM. So how to achieve it? You use one mirror. So as a result, to follow this product, we go for what is called the hexagonal mirror. Now mirror is not a linear mirror, it is a hexagonal mirror. So means that you can reduce the speed by 1/6. At one time, one part of the mirror will come. So this is a mirror. Instead of the linear mirror, we have the hexagonal mirror. So when one rotate it, so it will reduce the speed by that factor. So if you use the hexagonal shaped mirror assembly, you can reduce the speed of rotation by 1/6 of the shaft. So it means it comes to around 3000 or 3500 RPM. That is generally achieved in the mechanical processes. So it can burst. So in such cases, the shaft would have to rotate at 1/6 of the speed, so around 3000 RPM, which are mechanically possible. So in the Ruby laser, they are mostly Q switch laser. So we get high power pulses from the Ruby laser. This is the only laser where one can apply this rotating mirror method. It's very cheap and reliable, but it is possible only, it's very slow. It is possible only if the lifetime of the state is very large. Otherwise, the spontaneous level will be depleted. Feedback will not be provided within the right time. So this is the one case. So in other cases, so in Ruby, we can use the rotating mirror method, but it is not there in other cases. In the 4-level systems, the lifetimes are of the order of nanosecond. Upper level maybe 100 nanosecond, lower level maybe 10 nanosecond. There is a difference of lifetime, and 4-level system allows for it. More the difference in lifetime, more will be the population inversion. But it is not in all the cases. Even it may be microsecond or nanosecond, but not in millisecond. Ruby, that's why Ruby is today it's very important laser. So another is now instead of mechanically it is not possible, but electronically it is possible. Electronic pulses can be generated at a very fast rate. Switch can be operated at very fast rate. So we use what are called the controlled gate, logic gates. Transistors, they can operate at very high speed. So we use what is called a voltage controlled gate. Rapidly switching the cavity from high loss to low loss. We use what we say as the doubly refracting or birefringent crystal. The crystal, this is a normal optic element. If the voltage is applied, it will be birefringent. If voltage is not applied, it is a normal crystal. Okay. So yesterday I showed you the birefringent material DF glass. Those who are in lab, when we discussed these magneto-optic effect last experiment, I showed there is it is a quartz or some DF glass which become birefringent when voltage is applied. So those type of this is the same process here. So we call these are the electro-optic effect or Kerr cell, Kerr effect. This is also Kerr effect. Magneto effect is called Faraday effect. So when the applied voltage transfer the electro-optic crystal into what is called a quartz base plate. It is a birefringent. So it will become a quartz base plate. Now quartz base plate, it will split a linearly polarized light into circularly polarized light. It will split the one component into two components. Now again these two components will combine. So when they combine, again they will produce the linearly polarized light. So we can go from linearly polarized light to circularly polarized light to elliptically polarized light to again to linear polarized. It repeats, the process always repeats. It repeats after 2 pi. So this is what the process here. Now initially you have a laser output, you have a polarizer, vertical polarizer. This is the electro-optic cell with voltage switch. So when the voltage is off, this is a normal crystal. When it is on, it becomes a birefringent. So we can say here, when voltage is on, crystal become doubly refracting. When it is off, it will not be doubly refracting. Now what will happen when when it is doubly refracting, the light is not allowed to pass through the polarizer. So Q reduces to very low value. So it is not allowed. Now it is when the light come here. In this case, let the light coming from the laser is unpolarized light. when it pass through this polarizer, it will become a linearly vertically polarized light, because it is a vertical polarizer. Optic axis matches with the vertical direction, so you will get vertical polarized light. Now when it will become a quartz plate, so this will split up into two circularly polarized beams. So here you will see they are the circularly polarized beam. In that case it is a left circularly polarized beam. It again depending upon the angle or phase. It may be left circularly or it may be right circular. Now when this left circularly polarized beam, it will hit this mirror, it is reflected back. So there is a 180-degree phase. Okay. So 180-degree phase means your left circularly beam will become right circularly beam. 180-degree change. You are going in this direction. 180-degree phase, you are going in this direction. Now when the right circularly beam, they will pass through this, and then they will again change into linearly polarized light. So from here, initially the linearly polarized light will enter here. It will split up into two components which are left polarized, left circular. They will go to this mirror. Now they will become right circular. Now when these right circular two components they combine, instead of the vertical polarized light, they will produce light at 45 degrees. It is not plane polarized. Because of all this process, left circularly and right circularly. So during this, this type of light will not pass through the polarizer. So feedback will not reach to the laser. So when it is on, feedback will not reach to the laser. Light is not allowed to pass through the polarizer. So Q is reduced to low value. So whatever light goes, it will not reach to the feedback. So it is high loss. So Q is low. Threshold laser will not. So cavity is switched off. Now when the switch is off, so this light will go and it will come. So it will reach the laser media. So in that case, the laser will operate. So when it is on, the laser is in the switched mode. When it is off, the laser is in the working mode. So during this period, the pumps are working. So more and more atoms are pumped. So as a result, when the beam will come, they will come down. So during this process, through this we can also get the large pulses. So again, the synchronization. The Q switching is synchronized with the pumping mechanism such that the voltage applied to crystal drop to 0 at the time when population inversion is at the peak value. So at the peak value, the voltage should come to 0. So feedback will be there. So all the photons will come back. Again, the voltage is on, there is no feedback. So it can repeat like this. So here two type of cells are used. We call these are electro-optic shutter. Either it is a Kerr cell or we have the focal cell. They respond to electric field. So mostly the focal cells are preferred because they need lower voltage. Kerr cell, yesterday I told you, they work at the high voltage. In lab, in order to see the effect, we have to apply a potential of 4 kilovolt to 5 kilovolt. But focal cells, they work at very, very low voltage. So they are preferred. So this is how you have a laser, you have a polarizer, you have a one electro-optic. This is the electro-optic shutter here. So you have a laser, you have a polarizer, you have a cell here. So here this is another mirror. So when the light, when the cell is on, so light will not come back. When the cell is off, the light from here it will go and it will come back from the mirror and laser action will take place. Okay? Any doubt? तो डाउट है तो आप यहीं पे पूछ सकते हैं. So We use the Q switching kit. So then another second approach is the acousto-optic shutters. So they are similar type of gates, but they are based on the quartz crystal and piezoelectric transducers. So we have a crystal with piezoelectric transducer layer over it. So when a RF signal of this much frequency is applied, so acoustic waves are produced in the piezoelectric transducer. You know, when you apply potential to piezoelectric material, they change the shape. So if you apply pressure on these piezoelectric material, they generate the voltage. It's vice versa. So if you apply this frequency RF signal, they will generate the acoustic waves, and these acoustic waves, they convert this quartz crystal into a diffraction grating. So when the light falls on the diffraction grating, what will happen? It will throw it out. So throwing the light out means loss increases, Q will be down. Threshold will be very, very high. So it will convert. So the acoustic wave, they generate diffraction grating over the quartz crystal. So when the light passes through this diffraction grating, so they split up, they go in all the directions. It will not go to the mirror. Only this small portion will go to the mirror. Large portion will go out of the cavity. So loss is very high. In this case, the Q is very low, so laser will not operate. So when RF signal is there, it is a diffraction grating. When RF signal is not there, it is a ordinary transparent material. So it depends how fast RF signal is applied. So in the first case, voltage was applied, the crystal become quartz base plate. But here it become a diffraction grating. So when voltage is on, grating is there. When voltage is off, grating is not there. So this is we have the AOS. They are called AOS. So you see here, this is the switch. This is the AOS. When it is on, the light will come and it will go out. When it is off, the light will come and it retrace its path. So this on and off this part has to be synchronized with the pumping, with the lifetime of the state. Okay, so we use the acoustic also. So in this case, when it is on, the laser will not operate. When it is off, the laser will operate. Okay, so we will get large pulse. So Q switching is the method. These electro-optic or acousto-optics shutters are used for these applications. Then we have saturated absorber also. That is another option. So saturated absorber, these are nothing but these are some organic materials, organic dyes dissolved in appropriate solvent, like our tunable liquid lasers, tunable dye lasers. So these materials, you see, these organic dyes, they are selected on the property that they are opaque when intensity is low, and they are transparent when intensity is high. We call it the bleaching of the dye. Dye is bleached. So initially, when you switch on the laser, photons are less. These are the only spontaneous photons, because it will take some time to cross the threshold. Initially, the photons are spontaneous photons. They will go to the dye, and dye is opaque. They will not come back. The moment with the more, as the pumping is going on, there will be more and more spontaneous emission. As a result, the dye will start bleaching, and at one moment it is totally transparent. The photons go and then they will come back. So this is how. So dye, it always recover. It goes from opaque to transparent, transparent to opaque. This is the, or generally you call it as the transmission coefficient. Transmission coefficient is very, very low in the first case. It is very high in the second. So we can use different type of saturated absorbers. So at the beginning, I mentioned at the beginning of the pumping, the dye is opaque. It block and cavity loss is high. And as the spontaneous emission increases, the dye is bleached and it creating a low loss, so laser oscillation will work. So it all depend the lifetime of the or the duration of the pulse. It all depend upon the recovery time of the pulse. From opaque to transparent, and when it is when the dye is transparent, photon will come, large pulse will come. Again, there is a small emission. There are less number of stimulated photons. Large pulse will come. Again, the population condition will be disturbed. So again, dye will become opaque. For that purpose, it is opaque. So it is opaque to transparent. So we have the transmission coefficient of these dyes. They changes from 10 raised to power -6 to 0.03 in a few nanoseconds. The recovery time should be of the order of nanosecond, lifetime of the state. Okay, so the effect is reversible also. So different type of Lico dye, one common name is DODCL. Is a dye which is used for the Q switching of the laser. So we can use these simple absorber dye. They are simple and inexpensive, but on the other hand, they are toxic also, and they degrade with the passage of time. There is a degradation of dye, and one have to replace the dye or to work with the toxicity of these materials. So saturable absorbers are also the condition. So the method we call it as the passive Q switching, because dye work differently. So dye it is there. So it performs this role. Because it all depends upon the property of dye. In the case of electro-optic and acousto-optic, they are the active element. If it is on, it will work differently. If it is off, it will work differently. But here, dye, it depends upon the input. If input is low, dye is opaque. If input is high, dye is transparent. So it is a passive case in this case. So different type of these are the Q switch. You see, most of the laser, the Q switch are used. These are the Q switch used in the laser. Similarly, in the lasing material, we use the saturable absorber in one of the before one of the mirror. This is your laser tube, and this is a saturable absorber. Many lasers they come with the Q switching. Especially these are the in the medical algae. This is the example of what you call as the tattoo removals. We use the high power laser to remove the tattoos. Professor Savla, he will discuss. So in many applications you need the high power and in the pulses. So this is the way of the Q switching. Then we have the cavity dumping. So Q switches, they are based on the one is the rotating mirror method. If the lifetime of the state is, in that case, the lifetime of our upper laser level should be large. So that our rotating speed should be matching with that. Then we can have electro-optic shutters, which are based on the birefringent materials. Then we have the acousto-optic shutters, where we have the piezoelectric transducer. We use the piezoelectric material and the quartz crystal. Quartz crystal is a fine quality glass. Then we can use the saturable absorber. So another method is the cavity dumping. So in this case, here we have the two fully reflective mirrors. So these mirrors are fully reflective. So what happens? Pump are working. Okay, the mirrors, the feedback is there, but there is no output. There is no output. So your laser is working. So in that case, when this is going on, suddenly when you will see when the population density is very high, suddenly this type of element, in between you have an element, this type of element is brought in between. Earlier you have a mirror, earlier this part is off. The mirror photons are oscillations are there. Now you bring it there at certain angle. Now light will come, photon will go out. So it is always at certain angle. The output is not from the mirror, but output is from 1 of the H. So in that case, your cavity was full, you brought this element, all the power from the cavity is dumped out. Again it is out, there is no output, cavity pumps are working, it will come down, the output will be out. So this cavity dumping is another approach. But in the cavity dumping, what is the difficulties? Your system is built up. If your switch will not come, it will explode. That much energy will be generated. You are not taking away the energy. It is totally, your material is totally hot. You are at the danger mark. So if, unfortunately, if it will not work, the energy will explode the system. So that is there is a limitation with this part. So we see the pumping of laser medium, the pumps they are operating. So suddenly a cavity element or beam deflector within the cavity, it will deflect the beam out of the laser. So it may be some sort of the grating or other things. So, but in the grating, if the only one wavelength will be taken out, we will take the narrow part. So all the dumping can be, it can be any element or any type of the deflector. So energy within the cavity is dumped off the cavity in a single pulse. So this is a cavity dumping part. So we have the Q switching and we have a cavity dumping. So what will happen? In the Q switching, oscillations starts building from 0 level. Then the gain, you have a loss, you have a gain is increasing. So when the loss comes down, the pulse build up when it is balanced. So the pulse will build up in that case. But here in case of the cavity dumping, pulse is already built up. When you bring it down, it will start coming. So here the duration will be less. So in the Q switching, oscillation do not start in the initial state. The cavity Q rises from low value to high value. But in case of Q switching, it will only come from high value to low value. So duration here is very, very narrow. It is a short duration. Almost half the Q switching. So in case of cavity dumping, it can be the nanosecond pulse. It is significantly shorter than the Q switched mode. So time will be reduced by almost half. So full pulse will be formed in the Q switching. Here it will from half the pulse. So cavity dumping rate lower energy pulse than the Q switching. Why lower energy? You are getting half the pulse. Area under the curve will be less. So laser that cannot be Q switched, they are operated in the cavity dumping mode. That is another option. So this is then we have the Q switching, we have the cavity dumping. Cavity dumping is used in few cases where you need very, very large output, or you are very precise in the setting. Then another part is the mode locking. So mode locking is another switch. Q switching, it produces giant pulses of duration 10 raised to power -7 to -8. So maybe of the order of few nanosecond pulses. So if you have a nanosecond pulses, naturally your power will be of the order of 10 to power 9 gigawatt of power. If you want more power, so it means the pulse duration has to be small. So we go for the technique of mode locking. It allows the generation of pulses of the order of 10 to power -11 to -12 picosecond pulses. So but in mode locking case, the phase mode locking, it is the matching of the phase. It is working with the laser itself, laser mechanism itself. So an essential requirement is existence of the multi-mode. Then only phase can be matched. So multi-mode part, so we generally know that in case of the laser, this is the process. This is the separation between frequencies, C over 2 mu L. Okay. Now basically here, if you have any ordinary wave resultant of number of frequencies, it depends upon the relative frequency, it depends upon the phase, it depends upon the amplitude. If phase is not matching, your output will not be moved. So if the phase is matching, you will get large output. So all these parameters, they are time varying parameters. So if you have a time varying parameter, if there is no phase matching, you will get different number of modes are there. They have phase difference of say delta n, and if you take the resultant of all these, this is the total amplitude, the phase will come into picture. So in that case, if you calculate the total intensity of this type of distribution, you will get average value of intensity, Ni. So you may get some noise, somewhere it is more, somewhere it is less. It is a noise type of behavior. But if there is a phase matching, so in the noise type behavior, you have a different fields of different frequency, different phase, and all these parts. So you will get maximum this type of output. This is the irradiation pattern. Somewhere you get more intensity, but not all the time. It will not be repeated because it is time varying. On the other hand, if you match the phase, now if delta is locked, there is no delta and they are of same phase. So in that case, if you find the resultant, there is no phase creation, and intensity will be n square E square, or we say it is n average. So more the modes, more will be the intensity. More is the phase matching, more will be the intensity. So in that case, you will see now the modes are phase matched. Different modes are there, they are matching at this position, they are not matching at this position, again they are matching at this position. These are the phase matching position. So wherever there is a phase matching, you will get the large pulse. Large pulses after certain interval. So by phase matching, you can get the large pulse. Now you have to see how the phase can be matched. You have to look for the criteria, look for the means, how to match the phase, because they are random. Otherwise, they are time varying, or all may not be in phase with each other. So one have to look for those. So this is how, if you have a phase matching, this is the gain of the material, you will get long pulses. So this is your normal behavior, random pulses, these are your mode locked pulses. So you will get large pulses after certain duration. So how to achieve it? There are different techniques. One is again the external method, modulating the loss of the cavity, like electro-optic or your acousto-optic behaviors. We can go for the phase matching. We can use those materials now. In the earlier case, we use those as voltage controlled gate. Now here, we have to change the phase. They will be used as a modulators. And we know in the modulation what will happen. A single frequency, you will create the side bands. A one component will be shifted into three frequencies. Say nu plus modulation index minus modulation index. So one frequency you will get the three frequencies. So then another approach is the saturable absorber. So different type of absorbers can be used which lead to the modulation. So I mentioned you can have the acousto-optic or electro-optic modulators. This is called the active mode locking. So when the modulation is on, they will behave differently. When it is off, they will behave differently. But on the other hand, we have saturable absorber. So it depends if noise type. Now initially, if the resultant field is unmatched, you will get some noise type behavior. When this passes on the saturable absorber, where there are the peaks, dye will be transparent. Where there are small value, it will be opaque. So that part where it is transparent, that will be amplified, other will be suppressed. This is a saturable absorber. So active mode locking, we use the Kerr cell or focal cells. but in the modulation form. Now they are not gate, they are not shutters. We have the electro-optic shutters, we have the electro-optic modulator. So here they will modulate. They are called the EOM or electro-optic modulator. Now what will happen? Below the frequencies, the frequency which are coming from the output of the laser, what is the separation of the frequency? Delta nu. Okay. So it means if there are 4 frequencies, all there is a separation of delta nu between each. Now you put the modulator. You modulate the frequency by a modulation index of delta nu. Same spacing. So you have a one frequency. Now the modulated part will fall on the second frequency. Another component will fall on the another frequency. So if you have a nu m as the central frequency, you have a nu m plus 1, you have a nu m minus 1. Now you modulate this frequency. The other component of this modulation part will fall on nu m1. The second band will fall on nu m minus 1. So these two they will be phase match. These two they will be phase match. This will be diminished because some part of will go to the modulation part. So what we do, the amplitude is modulated by nu m plus delta nu or nu m minus delta nu, and below the spacing of different frequency, they are separated by this. So by this part interspacing, these are the frequencies. Now this frequency will modulator to these one. Now this will fall on this frequency. You see, these are all the lines. Now this is the modulator part. So if the modulation component of this frequency, they will match with this or they will match with this. So they will be amplitude, they will be added. So these two pulses, they will grow. This will diminish. So 3 modes are mod law. It's clear? So the modulation index should match with the spacing between 2 frequencies. Then they will fall on the same line. Now when these frequencies, they will again pass through the modulator. Again the sideband, they will also split. They will be also modulated. So this frequency, the frequency which was first nu m minus delta nu, now it will be nu m minus delta nu minus delta nu, or nu m minus 2 delta nu. Now this will match with some another frequency. So this process continues. So as a result, we get the mod lock. So mod locking is achieved if the modulation index matches with the frequency separation. So one use the modulator for these applications. So then another part I mentioned, we can use the electro-optic modulator, or there can be acousto-optic modulator. They are based on the similar pattern as your electro-optic shutter or electro-optic or acousto-optic shutter. So here it involves the modulation of the. So on the other hand, same method is applicable saturable absorber. So again, these are different type of dyes. So again, we know initially the laser emits spontaneous radiations, and the field of this, it behaves like a noise-like behavior. So when this noise-like behavior falls on the saturable dye, where the amplitude is less, dye is opaque. So no feedback. Where somewhere the noise level is high, the dye will be transparent, it will pass and it will come. So that only where the amplitude is more, that part will be amplified, rest part will be suppressed. So the role of separation dye is same there, only difference is that here we need the dye with the fast response. Different type of material, this is how it happens, the gain. So if this is the gain medium, this is the saturable absorber between one of the mirror. So in one case, when the intensity is low, so the light will not come back. When intensity is high, it will come back. So it all depends. Now here the separation depends where the in the noise like behavior where the noise amplitude is moved or where the intensity is moved. So as a result, in this case the cell become opaque immediately after the pulse is passed. Because after the pulse there is again noise. So you have a some more amplitude, then there is noise. When this amplitude pass, intensity is low, your observer will be opaque. Again another noise pulse will come, you will get. So this is how we get this. If you have this type of noise, now when at this portion dye is opaque, then at this portion dye is transparent. Again there is a small noise. Again dye is opaque. So during this portion you will get the pulse. Next pulse you will get the next pulse. So again in this case the duration of the pulse become depend upon the repetition of the noise pulse, repetition of the or the time variation of the electric field. So we have the saturated order, the strongest pulse will grow faster and less intense pulse will be suppressed with the passage of time. So we have another dyes. As a result, the laser output consists of regular pulses. Okay, because why the amplitude in the noise, why at certain places amplitude is more? It is because at those instants there is some phase matching. That's why those modes are locked. That's why here we give the concept of mode locking. Otherwise, saturated observer behavior is almost same in the Q switching or in the mode. So these are the different techniques, and now I come to the conclusion part. So for high power pulses, we can use the technique of Q switching. Q switching can be achieved maybe by the rotating mirror method or by electro-optic gates or acousto-optic gates, or we can use the another technique which is the cavity dumping, then the mode locking. In the Q switching, we use the electro-optic or magneto-optic material as the shutters. So the gate is open and gate is closed. Whereas in the mode locking, they are used as a modulator. So they modulate the frequency and they burn. So, or we can use the opto-optic devices just for the tuning. So for power getting high power, we have these techniques. For tuning the frequency or for the single mode application, we have the different devices. So for any requirement, for any practical application, the output need to be controlled or tuned, and accordingly one have to use something. So you will in the literature you will find we have the Q switch lasers, we have the cavity dump lasers, and we have the mode locking. Generally Q switching and mode locking, they are more preferred as compared to cavity. So we have the single mode lasers also, we have the single frequency laser, single wavelength laser. So single frequency and then single mode. So all these type of variations are required in the laser output if they are used for wide application. So these are the references I mentioned. You can have this very good book by laser theory and application, laser and optical instrumentation by these Nagabhushna and Satyanarayana. Then on the internet you can go to this is a very good site with physics based on the laser component. Then on Google search you can find a lot of material related to techniques. Different parts will be available. So I stop here. Thank you very much for your patience listening. And now, in case you have any doubt or any query, you are most welcome. And doubt from audience on the class? Anji. You understood everything or it was totally blank? Because it should be of your interest, because you are all engineers. Many of you are engineers, and it involves all your instrumentation or electronic part. So even if in the laser we use some, but yesterday Dr. Rajkumar mentioned parametric oscillators. So in case of the, you can go for a non-linear type of material. For example, if you have an ND JAG laser, it gives you a output at say 1060 nanometer. But when it pass through this anharmonic oscillator, you can get half the wavelength, twice the frequency, half the wavelength. You can also get 532 nanometer from ND JAG laser. So it is only from the laser and then with some comfort. So, madam, just देखना, you move to some center, maybe Guru Nanak Dev University, Gurdaspur.
Thank you very much, sir.
Thank you. You have any query or any question?
The lecture was very informative, sir, regarding the laser cavity resonator design techniques and some of the mode logging techniques. And it was very new for us and very beneficial for research scholars and faculty members. Thank you very much.
So, no question from your side. So, second center, MIT University, Gurgaon. MIT University, Gurgaon.
Good morning, sir.
Good morning.
Very nice this session, and we have one question from Dr. Bridges. He is from Nanoscience.
Okay.
Hello.
You can ask your question.
Yeah, question is regarding, you are showing about saturable absorption. So this guy is using as a saturable absorption, and this is of course old stuff people are doing since a long time. So what about the nowadays this graphene that is also very good saturable absorber?
Okay.
So what is your opinion how this graphene can be utilized for mode locking and this to switching purpose also? Means I just want to know what is the possibility of commercialization with this.
Definitely with the new technology, possibilities are always there. The nanotechnology is a new area, and people are trying how these material, graphene or carbon-based material, they can be utilized for specific application. Definitely, work has to be need to be done in how they can be utilized for these applications.
Okay.
There is no limit for any material to be utilized for any application.
So do you think graphene can replace with this dye?
It may be. I cannot claim, but it may be.
Okay.
Because it is a
very
wonder
good
material,
absorption property.
can do anything.
Okay. Thank you for your comment.
Any other question from MIT University?
No, sir. It's over.
Okay. So thank you all the participants. Now we go to the Jaipur Center, Shreyas Gyan Vihar University, Jaipur.
Hello, good morning, sir.
Good morning.
Sir, thanks for a very interactive and informative session. And there is no question from the audience. So, sir, thanks for.
Okay, thank you. So JEC College, Jaipur.
Good morning, sir. Good morning, sir. Yes, sir.
So do you have any query or any question?
No, sir, I don't have any question.
So you understood all the techniques which we have
discussed?
discussed?
Sure. We are getting each and everything, whatever you taught.
Okay. So thank you very much for all to all the participants. Now there will be tea break, and we will start after 10 minutes. So now it is it is 11:25. So we will start at 11:40. 15-minute break.
We will come back within 10 minutes.
Okay.
We will come back within 10 minutes, sir.
So be here at 11:40. Thank you very much all the participants.
You're welcome, sir.
मैडम वो लगा दीजिए टी ब्रेक. हाँ नहीं अभी लगा Good morning, participants at different nodal centers. I hope you are back after tea. Guru Nanak Dev University, Gurdaspur. तो जाइए सेंटर सामने लगा देते। Guru Nanak Dev University, Gurdaspur.
So good afternoon, sir. We are back, sir.
Okay, okay. MIT University, Gurgaon. MIT University, Gurgaon.
Yes, sir.
Professor Vivek Birla, participants are there after tea.
Yes, sir. Participants are there.
So can we start the session?
Yes, sir. Yes.
Our centers are Jaipur, Sresh Gyan Bihar University.
Yes, sir. Yes, sir.
So you are back after tea?
Yeah, sir. Sure. Start.
Okay,
sure,
okay. Okay, we are going to start the next session. So as per our planning, we have the next session that will be on semiconductor lasers and optical fiber communication. So we discussed about solid state lasers, we covered gas lasers and also dye lasers. So these are the lasers which are based on solid, gas and liquid materials, and in brief we have also discussed their applications, and mostly these lasers they are used for industrial applications, and I discussed about the control of laser outputs. So they are used in conjunction with those lasers. We use some techniques to get the desired output of these lasers. So now another laser which are the semiconductor lasers. I mentioned in the first lecture, we can have a semiconductor lasers on the same pattern just like solid state, gas or liquid laser, but specifically for the communication application, those are not very much suitable. As a result, we need a semiconductor laser which is very compact and compatible with the optical fiber. So very tiny lasers, and mostly these are the diode PN junctions, and here they are based on some input current. So they are also called injection laser diode. So pumping is by the electrons, by injection of the electron. So those electrons, now if the injection current is more, power is more. So there is always a threshold level, so that the current should be, the minimum current applied should be more than the threshold current. Then it will operate as a laser. So if the threshold current is, if the current is less than the threshold value, it is just like as your LED. So LEDs, they are based on the spontaneous emission. LEDs or laser diode or injection laser diode, they are based on the stimulated emission. So we can switch over from spontaneous emission to stimulated emission just by playing with the threshold value. So and these semiconductor laser, the injection current need the modulation. So for any communication application, modulation is must. So there should be some input parameter where I can superimpose my input signal, and then the laser output or optical signal, it acts as a carrier. So for communication application, we need a carrier, we need a signal, and it pass through the any of the communication media, and at the another end again it is the demodulation. So modulation and demodulation, for that purpose we need the input parameter. So optical communication is also the another area which was totally waiting for the lasers or coherent source to come. Otherwise, if you look at the optical communication, it's a very you can say it starts from the existence of humans. We have the optical signals. Fire is one of the optical signals, but source is not sufficient. It is not sufficient for long distance communication. So with the availability of lasers, long distance communication has acquired a very special place in the communication, and today you will find all most of our communication system, they are based on the optical fibers, optical fiber communication. It is all because of the availability of laser, because of the availability of semiconductor laser. So for this session, we have with us Professor J.K. Savra. He is ex-scientist from CSIO. Professor Savra, he worked at different organizations. Initially, he worked 8 years as a at the PGI, Postgraduate Institute of Medical Education and Research, as in the Biomedical Instrumentation Division. So he worked with the instrumentation there in collaboration with the surgeons or doctors fulfilling their requirements. Then he has around 30 years R&D experience as scientist, and at CSIO Chandigarh. He ultimately retired in 2007 as scientist G from CSIO. His area of specialization is R&D in electronic instrumentation, optoelectronics and fiber optic systems for short and long haul applications, fiber optic sensors, instrumentation for nuclear and strategic applications. He has developed different technologies, fiber optics, OLTEs for Army, 32 channel MUX for deployment of desert under a Planarian project, fiber optics containment, penetration assembly for nuclear thermal power plant, IGCAR Kalpakam, fly-by-light tail rotor control system for advanced light helicopter of HAL Bangalore, puppers for Kometa class Russian warship installed in naval warship at naval dockyard at Bombay and Visakhapatnam, intrinsically safe fiber optic voice communication system for coal mines, and these systems they were installed in Tisco colliery at Malkera near Dhanbad. Fiber fence, so fiber optic intrusion detection for strategic application for BSF and Army, and also developed underground fiber optic intrusion detection system for using speckle technique, fiber optic landslide monitoring system for hill rocks just to check the damage of the rock or weakening of the hill, fiber optic level, rotation, temperature, pressure sensors using intrinsically based sensing EFPI and FVG sensors. He has 2 patents to his credit. Professor Savra has is also a management expertise. He conducted many programs at CSIO. He managed and executed CSIR program on youth leadership in science. This is CP by LS, similar to Inspire from its inception in 2001. It motivates brilliant students to opt for pure and applied sciences as career. He participated and interacted with 7 Nobel laureates in Inspire 2013 at IIT Allahabad. He actively interacted with national security agencies such as BSF, CISF, NSG, IB, CBI as fiber optic perimeter security expert. So, and he involved in different type of trainings and HRD activities. Mostly he used to impart 6-month training to students as major projects to IIT students, BITS planning students, PEC students, Thapar Institute of Engineering and Technology, Patiala, and many final year students in designing their major project in the final years. Delivered expert talk in different faculty development program conducted by National Institute of Technical Teacher Training, NITTTR Chandigarh, and many other organizations. Delivered popular lectures at fiber optics at various institutions for popularizing science, and he also has a membership of different professional societies. He was chairman Computer Science Society of India Chandigarh chapter. He was the honorary secretary IEEE Chandigarh Center. He is member IT Club, IT Park Chandigarh. He is member Institution of Engineers, India, Kolkata region. He has also member Instrument Society of India. Professor Savra, he visited abroad many countries like USA, Canada, France, and UK, and gained a lot of expertise in area of optical fiber optic sensing and communication. So Professor Savra is very expert in this area, is a eminent person in the area of fiber optics and communication areas, and also in the instrumentation related to based on the lasers and optical fibers. So I'm thankful to Professor Savra for accepting my invitation and be with us for sharing his experiences. Now I request Professor Savra to start the session.
Good morning, and thank you, Professor Chaudhary, for such a elaborate introduction, which probably I do not deserve. But let me say that today's topic is very appropriate for all of us, in the sense that if we take away the semiconductor laser out of our life, somehow, or if it had not evolved, then forget about fast internet, what we say, digital world. All these things will not be possible, because with light sources of the type LED, communication is not possible without 4 to 5 kilometers. More than 4 to 5 kilometers, that is the limit. And with wire communication, you would have gone up to say 20-30 kilometers, or even 40 to 50 megahertz or megabits. So semiconductor laser in that way is very, very important to us, and I will concentrate more on its application oriented things for communication. So let's begin. See how it all started. In 2012, this field of optical communication was recognized by giving a Nobel Prize to Charles Cow, who worked in England, and he was awarded for what he did something in 1962. He demonstrated that optical fiber can be used for communication. He, along with Narinder Singh Kapani of India, they were students of John Hopkins, and they demonstrated that if optical fiber can be made transparent enough, then we will be able to communicate over it. And Corning took the challenge. Within a year, they developed fiber which was 4 dB per kilometer loss, and Cow and Kapani, they could demonstrate that it can be used for communication, and people have never looked back. Cow, in his Nobel Prize lecture in 2012, this lecture is entitled "Sand from Centuries Past, Sand Future Wise Fast." He said this because optical fiber is made up from silica, and silica is nothing but sand. And sand is, but deserts are full. Even if there is no sand, you can take sand from the soil by sieving, or there is always sand content in the soil, and this is there since the earth has come up. So his lecture, if you can get it on YouTube, he tells how sand has revolutionized things as far as communication is concerned. I have shown a small picture below. This YouTube is also available. How he demonstrated that light from a laser can pass through optical fiber, and if you modulate that light or you vary that light, that variation is conveyed to the other end. So he proved that this can be. What he had at that time was only a helium neon laser, only 2 meters of optical fiber and a detector, and he could demonstrate, and now you can see how we have progressed. I will try to show you something where people are talking of Google Fiber, which will give you in next 5 years or so 2 GB at your home, 2 GB speed, internet speed at your home, and quite affordable. It is already there in couple of cities in US. So once this field was recognized, another Nobel Prize 2014 came to the same field of photonics. 3 Japanese, Akasaki, Hiroshi and Shuji Nakamura, they got Nobel Prize for developing blue laser. So blue laser is also something, you cannot live without it now, because all your CDs, DVDs, they can be written only if you have a blue laser. So once you had blue laser, then only you could do this. And then it has got numerous applications in LASIK, the eye surgery, and for cutting and other things. So they got this prize for blue lasers. But remember, success never comes, so easily. These people, particularly the Japanese, they were thrown out of their job way back in 70s because they said you are working on a useless thing. This blue laser is something useless, and he was thrown out. Even the expenditure he had incurred in developing in the lab, and he said you have wasted the time of the lab, get out. And imagine that particular, he kept on working and developed it, and that he got a Nobel Prize, and this is something which will be a major contribution to communication also. And this blue laser, it is so common, as I said, writing CDs, DVDs, our music players, and so many things. Even in Diwali, many accidents will not happen if you have a pen drive size blue laser, and with that I have shown in the last portion, you can ignite the pataka, the anar, the bomb, with light. And it is already, you can make it, if you have a look at the YouTube, making a blue laser explosive fire. The optical communication, as you all know, what we need is a light source, as Kao had predicted or shown, then an optical fiber through which this light can pass, and a detector where the light will fall. Okay, so the detector where the light will fall, and any change in intensity, frequency, polarization, phase can be detected. So you have so many options. In case of light, you can change intensity, you can change phase, you can change the frequency. Frequency means the color, and you can, if you can detect that, you can detect what signal you sent from here. Yes, so this is how from a source the light goes into optical fiber, and then it goes to the detector and can be detected. Now this length of fiber can be 100 kilometers. Then you will need a repeater, and then that means you can go round the globe through optical fibers, and that is why the communication is cheap between, say, different countries of the globe. Transatlantic communication and all these prices of STD and other things have fallen down because we have a optical fiber laid through the seas also, under the ocean, and it is much cheaper than the satellite communication, more reliable also, less power, because you need a lot of money to launch a satellite for this purpose, and optical fiber once laid can work for decades. Fiber even laid in 1980 is working. So but all this will not be possible if we don't have what we say source, and source which can deliver enough power into fiber, and that is semiconductor lasers. Now I will talk about Google Fiber. as I said at the later when I come to communication. Let's see how semiconductor laser evolved. First of all, the first source of light was sun, then the candle, then the fire, and all those things. First solid state or something, not the fire, but the bulb by Edison. And for a very long time we had bulbs, but maybe very, very small bulbs at the most. But you can't light from a small bulb into optical fiber. Then they came out with the semiconductor light source called LED, which now is available for about half a rupee. Light from even LED, which was available, could not be launched into optical fiber. But once Kao said that a communication is possible, they said, why don't we develop LEDs with the following materials like aluminium, gallium, Indian arsenide, phosphorus, gallium arsenide, aluminium, gallium arsenide, all these, and they will emit different colors light, not only red, but different colored lights will be emitted by these materials. So they started working on this. At the same time, they put a small miniature lens in front of LED, and they made the LED in such a way that a very sharp beam will come out of the LED, which can be coupled to optical fiber. But there was a limitation. In the beginning, when LED was used as a light source, if your LED is having about 5 milliwatt energy, only 20 to 30 microwatt you will be able to connect to optical fiber. And optical fiber being, and that only to multimode fiber, and where the core is more than 50 micron, 50 or 62.5 or 80, then only it will be possible to launch light from a LED into fiber. Forget about single mode fiber. No light is possible to be launched into single mode fiber which will even travel 10 meters. Because you will be able to launch light of the order of nanowatts into an optical fiber with LED. So people were looking for something with which you can launch about a milliwatt of power into optical fiber so that it can go to 100 kilometers or more in optical fiber. So they started working on that. And laser, as everybody says in all the lectures, that laser, people were waiting for laser. And applications were there. You know something, if I get that, we are waiting for money. So if I have money, I already have a list that I will do this, I'll do this, I'll do this, I'll do this. Similarly, scientists were waiting for a laser. Once they said we will be able to do holography, we will be able to do etching, we will be able to do cutting, we will be able to shoot a satellite in the air itself, we will be able to destroy a tank without gun, with the light. All these people who know all sorts of applications were waiting. Same way, people in the communication were also waiting for lasers. And when then people are waiting for an application, people work because they will make millions of dollars if they invent that. If that is, and if they improve upon it. So a whole field evolves around lasers, and one field was for communication also. We'll see how fast and how things are, because it was in 1962, just 50 plus 3, 53 years back, that a solid state laser diode was created, was shown. And in 50 years, where it has taken us, you will see. The work started at IBM, and this was to replace gas lasers in many biomedical applications also, as I will talk tomorrow, how this solid state laser has replaced gas lasers. So what is a laser diode? Basically it is an electrically pumped semiconductor laser. What I have shown is a helium neon laser in the picture, how big it is, and the solid state laser or semiconductor laser is just the size of any transistor, small transistor that you use. 4 times 2 and 4 times 222 or 2 and 912 or that kind of a small transistor size device is a laser now. And how we use it for communication we'll see as we evolve. So these are some of the laser diodes, the size you can see for yourself, how small they can be, like any other electronic device. The difference is that at the end of this is a glass window instead of opaque metal as you have in transistors or other things. There is a glass window so that light can come out of that, and light necessarily will not be colored. So if you look into a laser, maybe it is emitting light in infrared range, and the next bad thing will happen, you will lose that eye. So never look into a laser. It may be light which is of the infrared, and particularly for fiber optic applications we use only infrared light because optical fiber is very lossy for visible wavelengths. Normally the first generation lasers that was required for fiber optics were in the range of 850 to 910 nanometers, which is near infrared but invisible. Then because fiber is more transparent, to 1300 nanometers. So second window came up, and then most of the lasers they were trying were for 1310, because at that time the dispersion is also 0. So they were developing for 1310. But optical fiber is even more transparent for 1550 nanometers. So they started developing solid state lasers or semiconductor lasers for 1550. So now the balance is between 1310 and 1550. Earlier, second generation devices they use 1310, and the present day devices they use 1550, because the light can travel 2 or 3 times more distance if you use 1550 for the same fiber. Getting back, the first commercial semiconductor laser was developed by RCA, Radio Corporation of America. They were making gramophone records, they were making radios and slide projectors, cinema projectors. RCA was a company, American company, Radio Corporation of America. They advertised their first laser by showing it that the light beam is passing through eye of a needle. That is a needle, and it is passing through that eye. So they said, first time we have developed a device in which the light beam is so sharp and small that it can pass through eye of a needle. In Christianity, you know, they say you have to be so pure, your soul has to be so pure to go to heaven that it should be able to pass through eye of a needle. Because it is so difficult to go to heaven that you should be so pure, because you are not having a body. It's soul and it should be so pure. So they said our laser light is so pure that it can pass through eye of a needle. And what Americans do, you know, when they find something good, they use it for our military. The first application of optical, the semiconductor laser, which was gallium arsenide laser, they used it for military applications. What were the military applications? For, you know, range finding. Where is the tank? So laser will be fired, and the beam will come back, and from the velocity of light that you know how much time it took, just like a radar. So you used for range finding, it was very more accurate than radar, because this beam is very narrow. For range finding, for secure communication through air also, and air-to-air missiles and infantry weapon systems. They first used these lasers for that. Then they gave for commercial application like communication. They passed on this know-how much later. First they used it for the military applications. Now if we look back, the light which is emitted by the material, the PN junction, when current is passed through this, is random. That's why if you see the LED light, whole thing is glowing. LED in the entire thing is glowing. And in case of a laser, the material is so arranged and the cavity is so arranged that the light is confined. It has the same phase, it has same color, that is wavelength. So this is through stimulated emission. This way, this theory, I think you have last 3-4 days been hammered how laser is different from another light source. I will come more to applications. These are the materials. Now the difference, in case of a solid state laser or gas laser, whatever, it had a material and then two sides were mirrors, and the light traveled to and fro between these mirrors, and when it was in phase because of the adjustment of the mirrors, and one mirror was semi-transparent, this was totally reflecting, then you got the lasing action. So what they had to achieve in case of semiconductor laser, they had to achieve this mirror also on the chip and this cavity also on the chip, and the material aluminum, gallium arsenide, etc., any Indian gallium arsenide, these chips and mirrors, and then the light would come. So what time it took was the material, and then for amplification, the how to etch the mirrors on the semiconductor device itself. So, and mirrors, what they do is they recycle the photon. So basic steps are absorption, spontaneous emission, and then stimulated emission, and then you get lasing action, which is common for all lasers. Here you could achieve a small chip laser on just a device, just like your transistor or any other IC device. First came the homojunction diode lasers. This terminology you will keep on getting repeated. You know, homojunction, heterojunction, vertical cavity. All these things will keep on repeating. Basically, if I try to simplify or rather oversimplify, it is like, you know, you make different sandwiches, submarines, and burgers and other things, by putting different layers of different say things which taste different between bread pieces. Same way, you know, using silicon wafers and materials, whether deposited or whether etched or whether sprayed, you create a chip, a sandwich type of chip with solid state materials, and when you give to it an excitation current, then a particular light is emitted in a particular layer. And how you change that light properties, or modulate or all those things, that depends upon the type of layers that you have put. To oversimplify for a student. But when it comes to making, it requires once again the complete VLSI technology lab to do all this. Same way the ICs are made, same way the very complicated type of ICs are designed and then sent to foundry. Here also the technique is homojunction. Then coming to the next, double heterojunction, means how the layers are deposited on the material. Then heterojunction. Then you have double heterojunction. So PN, NPN, PNP. Like this, you would arrange the material in such a way. And then this is a double heterojunction. Just see the basic two layer. One will be the material will be the top from where you will give the current. Two electrodes. In between will be different layers of different P and intrinsic, P doped, N doped, those materials arranged in a particular way. And then just from one end, the one of them light will be emitted, and you will like to tailor that light, its beam size, its wavelength, its other properties, using all other techniques of the VLSI technology. So you will keep on hearing these terms. How it is made, you have to read a theoretical book about how to make lasers, but I am emphasizing on how to use lasers. Then whether it is like a submarine, whether it is like a ordinary sandwich, whether it is like a burger, same way, whether the light is coming from the vertical end of it. Ultimately, if it is vertical, you can make it horizontal by putting like this. The vertical, light is coming vertical, you can put like this. So vertical cavity, it has certain advantages. Horizontal cavity has different advantages, and that way we can make the lasers. Other technique that you would like to use is, after all, every time you want to get the same wavelength, that all the devices should have same wavelength. So whether it will be a distributed feedback, how you will try to arrange the wavelength of those light. This is what Dr. Chaudhary in his initial lectures has said, that using different materials you will be able to tune to that particular wavelength. Other wavelengths will be absorbed by the material, or a particular wavelength will be emitted, and wavelengths that you don't want to use, they will be absorbed. So one way is using different materials. Other way is how to arrange them, how to arrange your mirror, where to arrange your mirror. So whether it will be a distributed feedback, say we will say in heterostructure, it will be different. We will be confining the carriers and light. I think I should have had a. Okay. So distributed feedback lasers are there. This term also you will keep on hearing. Then distributed Bragg reflectors, how they have arranged the mirrors. So to get a particular wavelength, so Bragg reflector based lasers. Then you have tunable lasers. For example, you want to change the frequency from one to the other. That is color of the laser from one to the other. And when I mean color, it is like, if I give an example, if you go to a cloth shop who is selling saris and blouse, you will see in the blouse section there may be 100 colors in green only, 100 types of colors in the red only, different shades varying from very little, and ladies can very easily go and show the sari and they will say, no, this is not matching, I want this. Even out in 100 they may say that it is not matching my cloth. Same way, it is possible to have wavelengths having a difference of only a couple of nanometers. So supposing it is 1550, you want a laser with 1552, then you want another laser by 1553, like this. So how you can make from this? So in order to tune the wavelength, some technology has to be. So Bragg gratings or tunable lasers, this technology also, by arranging the mirror and the materials, and then that laser should always be having that wavelength. Once you tune it, it should have that wavelength, it should not change. Because I will tell you why it is important when we discuss DWDM, dense wavelength division multiplexing, where many wavelengths are traveling together through optical fiber, and each wavelength is having communication of one city or one area. So they should not mix with each other. We should be able to separate them, although they will travel together. So like everybody is having a name, address and everything, where he wants to go, but they are going through a same path, same tube they are traveling, but there they separate out to their destination because they have that. Same way, different wavelengths should be able to travel together, and when you separate them, they should have the information on which was sent on them. So that's why we need tunable laser diodes also. So this technology also has been perfected. Then what are the challenges? As I have said in this, that you should have a wavelength stability. Wavelength should not change over time, and beam profile should also not change. The beam should remain same throughout. It should not broaden. To remind you, supposing I have a laser which is very, very good, and if I project it on this, you'll see a spot. Right? But as it goes further and further, the spot will become a circle, and circle will become bigger circle. If I have a very, very precise laser and I point it to the moon, this circle will be of the size of a football field. So it is not that the laser beam does not diverge. It does. But in case of fiber, the fiber itself is 5 to 8 microns, the core through which the laser is traveling, and for 100 kilometers or so, it should not divert much. So beam profile is important, and the wavelength stability is also important. As I said, it should not mix with the neighboring wavelength, otherwise then you will not get the signal that you were sending hundreds of kilometers away. In order to make life simpler, not only semiconductor lasers are made, they even put a pigtail. They put an optical fiber also along with it, into it when manufacturing. So you can see that we don't have any pointer. है मैम pointer नहीं है? There is a pointer. Just give me 1 minute. I have. Yes. So I got it. वहाँ नहीं जाएगा. ये इधर से चल नहीं रहा. Not able to move it. Move the pointer. Mouse लगे नहीं. Okay. So you can see the layer from which the light is being emitted. If we can connect an optical fiber there itself, then it will be possible. So if we connect an optical fiber in the IC or in the device itself, then you will not have to focus the fiber onto light. That is fixed. Pigtail, pigtail you know. So that pigtail is there, and now what you have to do is this end of fiber only you have to join with your fiber through a connector or through splicing or other things. So pigtail devices are available so that you don't have to worry how to put light into fiber. That is done from the factory. So best coupling is done from the research. Jaise some tap and then already some pipe is also joined to it. So you just put it to the water and that jet of water will come out of the end. You don't have to do that. So fiber also, the best coupling is done by the company and they give you. So pigtail devices are available. I will show you this. Then we will also have to package the device. It should be possible to handle it, because otherwise it's just a dot. The smallest bindi available is also much bigger than the size of the laser chip in the device. So you should be able to handle it. So, and then in order to handle it or in order to use it, you will have different 14 pin or 12 pin or 6 pin or 8 pin device. So you have to package it in that. And then earlier, because we were not having devices with pigtail, so we had a connector also attached to the device so that you can connect the fiber to it. Now I will go a little aside. Just as superconductivity, if we can have superconductivity at room temperature, then you will have monorails and motors which will not consume any electricity and still work and all those things. The room temperature superconductivity is still a far thing. Same way, the lasers, when they were made, they were not operable at room temperature. You required minus temperature for lasers, and unless they are operable at room temperature, you cannot use them easily. Earlier, I remember when we had computer, जैसे एयर कंडीशनर पहले लगेगा तब कंप्यूटर आपके रूम में हम इंस्टॉल करेगा. कंपनी वाला यूज्ड टू से. Now computer can be used anywhere. So they have made their devices in such a way that they can withstand temperature. In lasers also, they have found a device called thermoelectric cooler, which is a Peltier element. And Peltier element, Peltier effect is a temperature difference created by applying voltage between two electrodes connected to a sample of semiconductor material. It is opposite of Joule-Thomson effect, just like thermocouple. When you put it into hot water or anything hot, it generates a millivolts. If you can connect a millivolt meter, then it will deflect. If I do reverse of that, if I pass current, one junction will get hotter and the other junction will become cooler. So instead of metal, if I use a semiconductor materials, then one side, if I pass current, one side will become hot, the other side will become cool. And this hot side, if I connect it to some heat sink, and this cooler side, if I put my laser diode, then I will get cooling. It's a solid state cooler. People are using it now for refrigerators in space. You will also have refrigerators without gas, and they are there. Actually, in BMW and other cars, they have one cup. You put in that, and below, because of thermoelectric cooler, it cools, so your cold drink remains cold, just from battery, and there is no gas. So refrigeration is possible with Peltier coolers. But in case of laser diode, the refrigeration required is only for a dot, a very small material here and here, and give some current. The upper one gets cold, and on that we put the laser. So it is possible to have now laser diodes working at room temperature. And actually you can have minus 40 degrees centigrade temperature also through these devices, if you can dissipate the heat from the hotter side. So going back to my earlier slide, the chip now, the package now has a thermistor to know the temperature and a control device outside to stop the current when the cooling has reached that temperature. So now a laser diode package has 2 or 3 things. One thing is how much light it is sending. So you have a diode to monitor a small portion of that. Signal diode they call it. So you can increase the current or decrease the current to increase the intensity based upon how much current it is giving, how much light it is emitting. At the same time, you can also control the temperature of the laser chip. And from outside you can stop the voltage or give the voltage when that temperature is reached. So that means a laser diode packing has laser diode chip to emit light, another small photodiode to monitor the intensity, and if it is increased, it decreases it feedback, and if it decreases, it will increase the current. So to keep the intensity also constant, and thirdly, to maintain the temperature of the device, of the laser diode, so that now it is a complete unit, and it's a 16 pin or 24 pin or whatever, common configuration. All you have to put it onto a PCB which is having provision for feedback, for control of temperature, but thermistor is on the chip, cooling is on the chip, and light emitting diode is on the chip. So for communication people, it is simple. All that you do is buy a device and put it, and fiber is also there. Put fiber to that, and your things start working. Give communication signal, and it goes on the. I'll show you another version of that. This is the Peltier coolers that we have, but in case of semiconductor diode, Peltier cooler will be of the size of a very, very small dot only. But these are available for refrigeration. Bigger Peltier elements are available for refrigeration, or as I said, for cooling a cool drink in a car and all. That is the size of, that is the type of application that you. So this will have, device will be like this, and this is the optical fiber coming out of it, and all the things are on the chip. So for whenever you will go to a telephone exchange or where you see the laser diode, semiconductor laser diode will be just an IC. Now industrial applications of these communication semiconductor laser also, you want to say stick two plastics together. All you have to do is just show the beam on two plastics like this, and they will join wherever because of the heat generated, and then they will stick. That is one application. Then you have in the laser communication, just like the barcode reader which they are using for your in all the stores to read the price, etc. Barcode readers. Semiconductor lasers only used. This is for soldering. You can put your PCB here, and with the help of laser only, the flux and all are already there. That you have to put, and you have to leave it. It will heat and then solder also. So these are used for soldering also. Then yesterday I was hearing the news. It says that after about 9 years, a satellite sent by NASA has reached the Pluto, and it will go further. But it is taking the nearest pictures of Pluto, and the satellite was sent 9 years back. Okay. Now it takes days to get if the satellite takes the picture to send it to Earth. It takes days. Why? Because it sends bit by bit. So they are saying that we don't want that much delay in the picture and what we get. So what they are doing is they are going to have optical lasers, sending the that information encoded into light, and then there will be repeat stations in the space. So that will get the light signal instead of radio waves, and then that station will relay, and that station will relay, and they have already done this experiment. NASA has already done this experiment. The thing which will take you a week now will take you an hour to get the picture. So these semiconductor lasers and others, they are going to be used for space communication also. The big idea is, it is vacuum, so there is no scattering, and then so light can travel very far. So you will have satellites. There's some satellite around Moon, then that will get and send it to Earth, or around Mars, and that will send to you. So space communication is also a very, very big application of these lasers. So the basic application, as I said, is in communication, for which semiconductor laser was developed. So we'll discuss some parts. I will like to ask you if you have any questions till this, or even the people in centers. Any, or should I proceed further? Anything you want to know? You can stop me also in between if you have any doubts. Okay, now I'll come to the main application of semiconductor lasers, for which I personally feel I came. Let us see how. I already said that a light source, which is going to be semiconductor laser, will send the signal given to it by modulating its intensity, phase, or wavelength, and then send it to the detector, which will once again demodulate and bring it to the original electrical signal with the circuitry after this. So why we are using these lasers? As they have very long life, thousands of hours, so few years they have a life. They are very reliable, tough, compact, lightweight, and efficiency of electro-optic conversion, as he was telling you how to modulate. So they have electro-optic conversion also, because low applied voltage. You can work a laser with 5 volts total circuitry including. Otherwise, breakdown is only around 1 to 2 volts. So depending upon, and 5 volt laser. Otherwise, initially when we were using lasers, we had to use more than 200 volts. So now 5 volts it is possible, and they are spectrally pure. That means I told you that you can have lasers which are only 2 nanometers apart, 1 nanometer apart. So that spectral purity is also achievable now, and how that has helped us in sending many wavelengths over optical fiber for DWDM, dense wavelength division multiplexing, I'll explain, and direct modulation capacity of the order of tens of gigahertz. Tens of gigahertz is possible. What is the direct modulation capability? See, if I switch on and switch off a device, then next switch on and switch off should be distinguishable from this. Supposing I do it 20 times, my eye will not be able to distinguish whether it is a continuous source of light or whether it is switching. So these laser diodes are able to switch on and switch off tens of gigahertz. So you can, the higher this thing, the longer and more data you will be able to send. More zeros and ones you will be able to. Optical fibers, as you all know, is an optical tube which is having 2 refractive indices, one in the core and another in the, which is different by 1%, and the light travels in the core, and cladding keeps the light into the core. Normally the outer size of the fiber is 125 microns and the inner core is 5 to 8 microns in case of single mode communication. Very roughly or crudely saying, the size of fiber is of the size of your hair. And 1 kilometer of fiber weighs only 14 grams. Just 14 grams of glass can give you 1 kilometer of fiber. And light can travel in optical fiber to about 100 kilometers where it can be detected. The detectors are available which can detect even nanowatts of power. So seeing all these advantages, then optical fiber communication has become now so important, and we cannot live without it. Probably the same type of life that we are living. Can live without electricity also, but not the same way as we are at home. You don't die, but we can't live like we live normally. Same is the case with this communication. If it is taken away, we will not have this type of communication available to us. So why fiber has come is it is cheaper, high speed, as we will see with Google, distance, weight, as I said, 14 grams can give you this size of your hair. So we can have hundreds of fibers in a very small cable, and freedom from interference because light is traveling, so no electromagnetic interference can go into it, or it is also not radiating any electromagnetic interference from outside. And electrical isolation, no current, no shock. No shock can destroy your communication also. And secure also, somebody will have to cut it, tap it, or do some very complicated things, then only he can tap the signal from the fiber, which you will also know. Just like your water pipe is, nobody can tap it unless he cuts some hole into it, then puts another thing and all. Of course, people have been doing with oil pipelines. The pressure drops, so they caught them. So they can be caught if you are doing something to the fiber. So security also is quite a major advantage of optical fiber communication. Let me not get diversified. Come back to our topic. So bandwidth advantage is there. As I said, gigabits can be sent over optical fiber. Attenuation is light can be carried very far away, 100 kilometers without a repeater, and thousands of these copper wires can be replaced with just one or two optical. Laser transmitters, they are very small devices. What they supposing we have an audio output, the simplest type, and just with a IC, which can be LM358 or 741. If you can change the intensity of this laser, which with your audio input, because there is a DC current flowing when there is no any output input, and this current can be varied if this bias changes. And we connect optical fiber through this, then that intensity variation will be sent to the in the fiber, and there you have a detector, and you can detect. So this is the basic principle of laser transmitter. Here is the laser, and rest is a complicated circuitry for gigabits and other things. But simple principle is this, that you are modulating the intensity of the laser with the signal that you. Then now let us talk of something I've been saying, WDM and DWDM. See, earlier what was being done was that light of a single wavelength was sent through optical fiber, and at the other end it was demodulated. Now you soon realize that the bandwidth that I want, the number of circuits that I want is now full. I'm not able to do it more. What you thought? You thought that I will put another fiber. So you put another fiber, another source, another detector. Then that is also full, so you put the third, just like highway. One is done, then you do the 4 laning, then you do the 8 laning. You keep on doing the laning. Similarly, you kept on adding fiber. When somebody said, what is the problem? The God sends us 7 colors for ultraviolet and infrared from sun all together, and Newton told us how we can separate with the help of a prism or with the help of a grating, and they don't mix. Those colors don't mix. They are there in the beginning. We can separate. We didn't know. Same way can we not? It is basically we are working with light. So let us do it with fiber also. Let me send 1310. Let me send 910. Let me send one more wavelength, and send through fiber. So what they did, they sent these two or three wavelengths. Now you mixed 3 drinks, Coca-Cola, Sprite and one more orange. You separate, उधर बोलो bottle में ले जाके you separate. Is it easy? It is not. So similarly, they said then we need devices for that. He said no, we have already gratings, we already have prisms, we will work on this. So they were able to separate. Of course, prisms, grating, they had to be, or interference filters or things like that. They already had, they only tailored them for optical fiber. And they were able to separate. So instead of 3 fibers, now they could use single fiber. So no more digging again, no more putting fiber again. So, but they will need 3 sources, and they will need detectors after separate. Grid and need, they go together. Then why only 24? Can we send 24 wavelengths together? Can we send more than 24 wavelengths together? So they said okay. First we called it wavelength division multiplexing. Now we will call it DWDM, dense wavelength division multiplexing. So you can have 24 sources of light being modulated by 24 stations of signals, or 24 telephone exchanges, or 24 TV stations, and then we will have one laser for each, and then we will mix them together, and then we will separate them there, and if needed we will also amplify in between where it is not needed. Supposing it is passing through some, I need it in Delhi only, and the signal has become weak halfway, then I will amplify also there without doing anything, without demodulating or things like that. I will amplify also and take it. So you tell me some way of amplifying also. And for that also laser came in for help to amplify without converting the signal into electric. So the DWDM systems have also evolved. Let us see how. So a WDM system transmits multiple data signals using different wavelengths, different colored light, and the capacity is increased by multiple. Jitne wavelength bhejoge, it behaves like that many fibers. So supposing I have 8 wavelengths, 1, 2, 3, 4, 5, lambda 1, lambda 2, lambda 3, lambda 6, and in between stages, supposing this signal is meant for say Karnal or Ambala, this is for Delhi, this is for Gwalior, this was different. I should be able to take away that signal, and I should be able to put signal of that station also for this to go. Just like train, passengers get down and another passenger from there, it should be possible to go. But it will be in this case it will be from a running train. You are not stopping anything. You are taking away the signal and putting also a signal. Signal is going at the same speed, just like that. It is not it is like parachute dropping somebody at that station and somebody coming in from another way. So they also evolved these and through fiber, and then here you have different detectors. I have shown another way of doing it, that you have client equipment lambda 1, lambda 2, lambda 3. The wavelengths are mixed. In between you have what is erbium doped fiber amplifier. I'll explain this. And then you are separating the signals, and these you have and taken out the signal also. So I'll skip this, or see that these 3 stations, they were having lambda 1, lambda 2, 3, blue, red and yellow. These were the signals, and then it came up, and then they dropped less, so EDFA was applied, erbium doped fiber amplifiers were used, and ultimately you got signal in good strength. Because up to this it has become very weak, and then EDFA will amplify it again and give you the signal. See this, you can see this signal has become for our use. This signal has become very weak, and here then with the help of EDFA we could amplify and regenerate the signal. So EDFA erbium doped fiber amplifier. See, I'll be coming to this. Actually, people, human beings are dreamers and then demanders also. Once you give them something, and then there are people who provide their demands or fulfill their dreams, and his dream is money or popularity or Nobel Prize or whatever. It could be anything. Need not be money only. It can be just mera izzat hona chahiye. I should get power. I should become Nobel laureate. Like this. So how it has evolved is that somebody said, "What is your dream?" I should be able to talk to my brother even in a forest in Africa. I said, okay. Then people have started working. Now he also has a mobile phone. You also have a mobile phone, and you are able to talk. If something happens to my daughter somewhere, I should be able to know. So now it is possible with the help of phone. उसका हार्ट बीट रुक जाए आपको पता चल जाएगा, कहाँ पर है ये भी पता चल जाएगा. So GPR. So these things are being added to facilitate. Similarly, fiber. He said you have so many sources. Then sources are laser diodes. What is this? So now we can have a semiconductor diode. A small length of fiber should be able to become source. We will dope the fiber in such a way, give the current, and so that it becomes a source. He said, okay. Then I should be able to mix them together. He said, I will put number of fibers, just like pipes, into one big pipe. But in this case, it will not be big also. Same size pipe, I will be able to put many fibers through a coupler, and you are able to put many light wavelengths into single fiber. Then he said I should be able to amplify also through within the fiber. He said okay, then we will put you a small 10 meters length of fiber which will be special, which will be erbium doped with erbium ions, which will behave like a laser, and I will push light into that 10-15 meters of fiber which will glow with that, and it will absorb energy from that. The fiber going there will absorb, and I will also provide you fiber Bragg grating based material in the fiber itself which will separate the wavelengths, and at the end you will have detectors with which you will be able to do that. So it is, he wants an all fiber system. Just one box, then everything should happen in within fiber only, and I should be able to get the signal there and amplify. And this distance can be from Europe to America, transatlantic, which takes 7 hours of flight. It should be possible with that, and it has been made possible. One big component in that is this semiconductor layer. Okay, let's see how I proceed further. So, as you ask, what is EDFA? I say EDFA is a fiber amplifier. You are getting a signal which has become weak because of absorption in the fiber. Attenuation has happened. I have a source of light which is at 980 nanometers laser diode. Okay, and this length of fiber, small length of fiber, which is about 10 to 15 meters, is doped with erbium. Its core is doped with erbium. So this light from a coupler is coming into this erbium doped. The electrons in this are getting pushed to the higher level, and when they come back, they give out light. The material is such. Now the signal which is coming from, weak signal which is coming from here, it absorbs energy from those electrons which are falling back to his wavelength, and it goes out strong. So to be very crude, I am running and somebody gives me a bottle and I of cold drink. I am thirsty, I keep on drinking as well as and after about some minutes I throw away. The same way they have provided with a small length of optical fiber, 10 to 15 meters, which is of erbium doped fiber amplifiers of this size. It will have 10 to 15 meters of optical fiber, bare fiber, need not have any cabling and all. Inside will be one laser diode, 980 nanometers, this one, this I'll be having, and another one also to push from the other side, two laser diodes, and then the signal here will go amplified. Of course, a small battery, 9-volt battery or something like that, which is chargeable. So I will have a box like this. The optical fiber is coming into this, which has weak signal, and optical fiber for our purpose going out is strong enough. The signal is same as what was sent. So that dream of having in-fiber amplifier, otherwise what they used to do earlier was that light will be coming here, then I'll have electronics here. So there will be a detector here. It will detect the signal. It will amplify that signal with amplifier. Then I'll have another light source here. That I will drive again, and that signal will go. The same was with electronic things also, electronic repeaters. So we were having first type of repeaters. Now that repeater, you don't have to demodulate the signal at all. The light signal itself becomes strong. So very small devices, they have been used as repeaters. Then, as I said, people want sources also to be, so they said, okay, we can make for you fiber lasers. The lasing can take place not outside in a chip to make a semiconductor laser. We will have all those materials in the core of the fiber itself, and will cause stimulated emission within the fiber. So you won't have to connect a fiber to the source. So this will be there. So we have a fiber to which we connect few light sources and make it a fiber laser, and then light will go from source. So you have something starting from the fiber, you are modulating that through outside, and then you are sending over there, your repeater is repeating, you are taking away through a coupler the signal for that city, putting the signal for that city into it, and there you separate them out into various signals, various lights that you were sending. I'll show you this. The movies I'll show you just after this. So I don't know whether I have been able to emphasize, but all that I wanted was that a laser diode specifically tailored for with semiconductor materials became semiconductor diode, and this semiconductor diode has fulfilled the dream of taking signal far away, increasing the bandwidth to gigabits. It has also fulfilled the dream of amplifying the signal within the fiber. It has also fulfilled the dream of separating the signal for that particular station, and also separating the different colors at the other end. So all this has become possible because of this semiconductor technology, and particularly tailoring those for semiconductor devices as semiconductor laser diode has solved our problems. I will show you a couple of movies. Movies जाएंगे madam उधर? Videos? Okay. But before I finish, just see I'm showing a picture. In this, you can see a box. This box. Okay. This was the laser, distributed feedback laser. when this child was this old, about 4 or 5 years, or 3 years old child, and this. And afterwards, just see, within a couple of, this was in 1995, and in 2002, this child only grew, and the laser has become, uski godi mein pada. It is in his lap. What is it? This much big equipment has become this much. So that is the kind of progress that has taken place in this field. Before I end, I will show you some interesting. हम थोड़ी मेरी मदद करोगे? वो मूवीज आपने करी थी ना? हाँ. How much time I have? Not 10 minutes or so? So first of all, show how semiconductor laser जो चलने का है. हाँ. I am now showing you a couple of videos. First is the inventor of the laser diode, Robert Hall, discovered in 1962.
It's a crystal, very much like gallium arsenide, a tiny crystal with mirrors front and back, polished with cleaved, so it was a largely reflecting surface on both faces. And you pass a current through the diode that populates the space inside the junction with electrons and holes. And these recombine and produce light, which is bounced back and forth through between the mirrors, and that inspires more electrons and holes to recombine and signals out, instead of a broad beam of spectrum of light, it concentrates at a single frequency, and all the light comes out in a very intense collimated beam.
Next, the comment. So this is how Bob, he showed how the laser diode works, or semiconductor laser works. Now see what this laser diode or the semiconductor laser has done. Everything is on a single chip, and many wavelengths you are able to mix.
10 electrical signals enter the chip, each one carrying data at 10 gigabits per second. 10 tiny lasers convert those signals into light. This is the electro-optical conversion at the heart of every fiber optic network. 10 conversions take place simultaneously on each Infinera chip. 10 modulators act like microscopic Venetian blinds, opening and shutting to encode the data onto the stream of light. Each light stream travels at a different color or wavelength, so the 10 channels
10 lights are combining together
without interference. Next, the photons go through 10 tiny optical power monitors, which measure the power of the light signal on each channel. The monitors control 10 variable optical attenuators, which regulate the power or brightness of each light stream. This photonic integrated circuit has a total data rate of 100 gigabits per second. But the benefits go well beyond bandwidth. Integrated circuits are more reliable than discrete components because the connections are printed directly onto the chip.
All are combined onto one fiber.
Integrated circuits are more cost-effective and easy to manufacture than discrete components. The 10 streams of light are now ready to be multiplexed onto a single optical fiber and go out onto the network. Today's growing volume of internet traffic requires a solution that's large and scalable, and yet small enough and cost-effective enough to suit today's metro networks, national networks, or international networks.
So you can see that technology has developed into something doable. So all you have is a chip. To this, you 10 cities or 10 countries or 10 locations. You connect the signal. That Infinera chip does that, and one fiber goes. At the other end, a similar thing, which is of the size of your laptop. Will yeah. Now you will see in days to come this Google, what Google network will do for you. Earlier one was like this. If you are downloading something, you have to stop. This was the speed with which we could internet earlier. One at a time. The line name yesterday, broadband. The future one. So this Google Fiber already in few countries there, it's already giving you 2 gigabits at home, and it will be available in all smart cities in the days to come. And you can see more details of Google Fiber, how they are doing at home premises, how they are connecting fiber already. So it has all become possible because of this small device, semiconductor laser. Any questions from them? That after.
So thank you, Savdaji, for very interesting and elaborating lectures on semiconductor lasers and optical fiber communication. So he has elaborated that how semiconductor lasers, they can help in getting a speed of gigabits per second or terabits per second. It is only possible that we are able to get semiconductor lasers of different wavelengths. So it is not possible to have 100 gigabits per second or 1 terabits per second on a single system, on a single wavelength. You need multiple wavelengths because there are the speed limits. On a single fiber, if you go into drill, it is the best performance of your fiber if you use it at low data rates, maybe 1 gigabits per second or 2.5 gigabits per second. If you are talking about 100 gigabit system, it means you can have 40 lasers, 40 channels, or if you are working at 1 gigabit per second, 100 lasers wavelength can be used. The system performance will be best in that case. So you cannot put 100 gigabits per second on a single wavelength. So multi-wavelength system is there which are fulfilling our requirement. Professor Savda, he described in one of the video presentation how all the wavelengths, they are combined together, and then using the multiplexing they are put on the same fiber. Similarly, they are separated at the other end. So it means you need those much wavelength. Either you need 100 lasers or you can have tunable lasers. So tunability can also be there. So all optical communication is very, very now important in the communication scenario in the area of ICT program, and they provide a broadband or huge bandwidth, which generally we call optical fiber system. They have infinite bandwidth. So it is possible, it all could be possible only with the semiconductor lasers. So again, I'm thankful to Savraji for giving very important information about all these semiconductor lasers and OFC. Now, in case you have any query or any questions, you are most welcome. May I ask क्वेश्चन फ्रॉम गुरु नानक देव यूनिवर्सिटी गुरदासपुर. मैडम देखिए थोड़ा सा. गुरु नानक देव यूनिवर्सिटी गुरदासपुर.
We don't have any questions, but I would like to say more about this particular presentation. I think hats off to you people. You are doing wonder for the society actually. Yeah, I'm talking about Mr. Chavda. He has a deep understanding of the subject matter. It's a really wonderful experience to be here, and I think due to these fellows, the country is surviving. Hats off, and thank you once again.
Thank you, Professor.
He explained what is recently going on in this area of communication. I hope he covered what you asked in the first session, that we should add what is the latest development in this area. So thank you, Gurdaspur Center.
Thank you very much.
So now we move to MT University Gurgaon. You have any query, or you want to pose any questions?
Hello, sir.
Yeah, hello.
Sir, in fact, I would like to acknowledge to the Chavda sir that he presented the session very well, both through the video and through audio mode, and beautiful presentations. And the concept we are shown for the wavelength part is very clear now. We had one or two queries, but suddenly the participants who were supposed to ask, they have to rush out for the DRC meeting. So if possible, we will send the questions to sir on the email, and if possible, he can revert back to us.
Sure. Definitely he will revert back. Otherwise, he will be with us tomorrow. If any doubt is there, he can get his doubt clear tomorrow also.
Yeah, sir. Sure, sir.
Okay, so thank you very much. We have another center, Shreyas Gyan Bihar, University Jaipur. Now we move to Shreyas Gyan Bihar, University Jaipur.
No questions. Thank you very much for a very informative lecture.
Okay, thank you.
Thank you.
JC Group of Colleges, Jaipur. Nobody is there? This is a JC. So thank you all the participants, and thank you Chavda ji once again. So now we will go for the lunch. So after lunch break, we will again connect for the lab demonstrations and one lecture by eminent professor from MT University Gurgaon. So thank you once again all the participants.
Thank you. I'll be coming tomorrow also for that medical application. So in case you have any questions out of this, it's difficult to cover.
Good afternoon. Good afternoon, all the participants at different nodal centers. I hope you are back after lunch. Please occupy your seats. We are going to start the session soon.
सर मैं अभी जाऊँ उनको भेज देता हूँ क्योंकि मैं स्टूडियो में जाना है
इसको भेज दो भैया, कोई आदमी जब चाहिए निकालो।
Hello, sir. We are not able to hear you. Hello, sir. We are not able to hear you.
अब बोलिए।
Hello. Hello. Good afternoon.
Hello.
इधर से तो बात कर लेगी यार। Hello.
Good afternoon, sir.
Hello participant.
सर आवाज नहीं आ रही है आपकी।
Hello.
Hello.
Good
Hello.
afternoon, sir.
Good afternoon. You can hear me?
Sir, you're audible.
Okay, thank you, thank you. We are going to start the demonstration soon.
अरे अभी बात करने दो। ठीक है।
Hello, sir. We are not able to hear you.
Hello.
Sir, we are not able to hear you.
Now you are able to hear me?
No audio.
You are not able to hear me now? I'm audible.
Sir, no audio.
No audio. Guru Nanak Dev University, Pradhanpur, I'm audible there. Madam Anu Sheetal, I'm audible there at your place.
Yes, sir. Hello.
Hello. Okay,
Sir,
okay.
you are audible. Audible.
Just I'm testing whether I'm audible at all the places or
Sir,
not.
we are able to hear you, sir.
Okay, okay. आगे
Hello, Ambedkar University.
Yes, sir.
Now I'm audible at your place.
Sir, we are hardly listen you because the sound is not clear.
Hello, sir. Now it is clear.
The sound is not much clear.
Now it is clear or not? Hello.
Little bit still there is problem, I think.
Let me adjust to some extent.
Okay.
Sir, what about now? Hello?
Now it's okay?
Yes, sir.
Now it's fine? Okay. Other centers, Suresh Gyan Bihar University, Jaipur. Suresh Gyan Bihar University, Jaipur.
बहुत कम आ रही है।
Hello?
आवाज नहीं आ रही है सर।
Hello, Suresh Gyan Vihar University?
आवाज नहीं आ रही है सर।
सर एक बार आप स्पीकर्स के कनेक्शन चेक करिए अपने।
From our side it's okay. You check at your side.
आवाज नहीं आ रही है सर।
आप अपनी साइड पे देखिए, अपना स्पीकर देखिए।
हेलो
हरजोत अपना माइक ऑन कर ले, एक बार माइक चेक कर ले।
माइक ऑन है यार।
और सच माइक तो ऑन है, मैंने सुन रहा।
आवाज बहुत कम आ रही है
सर। आप अपने स्पीकर्स के कनेक्शन चेक कीजिए सर,
क्योंकि सर यहाँ पे आवाज बिल्कुल ठीक आ रही है। मैं क्लासरूम में हूँ।
ओके, परमजीत बोल रहा है जी।
हाँ जी
हाँ जी, मैं क्लासरूम में हूँ ना, तो बिल्कुल सही आवाज आ रही है यहाँ पे। उनके लोकल एंड पे प्रॉब्लम है
सर। उन्होंने एक बारी फोन करके कह दो कि ना स्पीकर्स के कनेक्शन
सर। आ गई आवाज।
ठीक है, ठीक है।
थैंक यू सर।
Suresh Gyan Bihar University, now it's okay? Suresh Gyan Bihar, Jaipur.
Yes sir.
Now audio is clear?
Yes sir.
Okay, okay. JEC Group of Colleges, Jaipur. JEC Jaipur.
Afternoon, sir.
JEC Jaipur, I'm audible at your place?
Yes, sir.
So good afternoon. Now we are going to start the session.
Yeah, sure, sir.
All set. Sure. Connected. Now we are going to start the demonstration. So friends, today we discussed about semi-critical lasers. Professor Savla, he gave a laboratory lecture on semi-critical lasers and their applications in optical fiber. Now we will demonstrate some of the semi-critical lasers which we are using in our laboratory, mostly for the optical fiber communication. So he must have discussed in the lecture that these semi-critical lasers, they are very small in size. They are made in such a manner that they can be a very useful source for optical fiber communication. And I mentioned that for communication we need a very compact source, and then it should have input parameter which can be modulated, or over which the signal voice or any other signal which is converted to electrical form, it can be superimposed over the input parameter which act as a carrier. So carrier and signal concept is there. So we mentioned the semi-critical lasers. You can have in this case they are very small. This is one of the semi-critical device. So here you will see they are always, these are the diode. You will see the two pins. So they are fixed on this connector. So you can imagine how small it is. And now we have this source which is mounted with the connector. Now this connector can be coupled to optical fiber. This is again a optical fiber with one type of FC connector. So we can couple the two and now they can be our optical link is established. So source to fiber coupling is always with the connector. So they are all the correct connect. Either these sources they are provided either with a pigtail or with a receptacle, so that our fiber can be connected with the device efficiently. Because launching of power at the input is very important. If you are using your signal at the input stage, you will not expect any good response at the destination. So as a result, manufacturer, they always provide these optical sources with some what you call they call these are the electro-optic devices. So with either with the pigtail, so that pigtail means you have an optical fiber at the end, so you can connect the two fibers, or it is with the receptacle. So I can put my connector and now link is there. So it is for the ease of the users, so that connectivity is not a problem. So then for further demonstration part, now we will start mostly in these characteristics. In any source, I should know what is input versus power characteristics, or electrical and light power characteristics. So when we apply some current, how much power is emitted? So we can see here these characteristics. Professor Chavda, he discussed these points. So today first part we will cover a LED and a laser dioide. We will see what is the difference between a LED and laser dioide. So he mentioned that whenever we start any system, initially when you provide current to a device, so what will happen? The current will not be enough to reach at the threshold level. So once current reach at the threshold level, we will get the stimulated emission. So this is the characteristics we have shown here, the current versus power characteristics or light output characteristics of a laser dioide. So initially when you apply the current, you see there is only stimulated spontaneous emission. The current will start exciting the carrier to reach at the threshold level, and after the threshold level you will see the laser start working. So as you increase the current, you will get a large light output, because when the stimulated emission starts, you will get the large output. So this is the characteristic. So this is the spontaneous part and this is the stimulated part. All our LEDs, they are the spontaneous devices, or they are called the incoherent devices, because spontaneous emission is incoherent. Similarly, all our laser diode or ILDs, they are based on the stimulated emission and they operate only after certain threshold. So here we will see, we can find what is the threshold current of the laser diode. From these curves we can find what is the threshold current. So whenever you have to operate your system, you have to apply value of current which is more than the threshold. And it is not, this region is also useful, and this is for the LED characteristic. You will see the LEDs, they are based on the spontaneous emission. So in case of LEDs, we will see when we will draw the curve, you will see whenever you start applying the current, in case of LED, the power goes on increase. It is a very ideal curve, straight line. But in practical, you will see this may not be exactly straight line. So we have to choose, and we know that mostly our device, they work on the linear region. We want device to be a linear device, so that whatever signal you apply at the input, you should know what should be output. So LEDs, they are the linear device, so we have to choose what is the region of operation of a particular device. So from this curve, from the experimental curve, we can find where is the linear part, the region where the curve is a straight line curve. Then similarly, when you draw the curve with the LED, you will see in the measurement, initially you will not get any power. So you have to go on applying the current, and after certain value, maybe at the threshold level, you will see a sudden rise in the power. And this sudden rise is because of the stimulated emission. It means once you reach at the threshold value, the stimulated emission starts. This is generally the curve for the semiconductor lasers. So we will move now to our other experimental kit. So this is we have this semiconductor based optical fiber communication setup, where we have a LED and we have a laser. Both LED and lasers are there in this instrument educational kit. So it has photo detector also. तो आप साइड आ सकते हैं, तो कैमरा will not capture otherwise. So now, if these two, they mostly these sources I mentioned, they are always provided with a receptacle. So I can apply any optical fiber or fiber pigtail. I can connect at the source, So these are generally the ST type of connector which are used there. Different type of connector are used in optical communication. We have the ST connector, we have the FC connector, we have the SC connector, LC connector. So many type of connectors are there. So this is one sort of ST connector. Mostly these type of connector they are used with the multi-mode fiber. So now we will connect this other end of this fiber patch cord with the photogrid. Okay. So initially the current is 0. So now if you in this case if you increase the value, somebody note the values. I will apply the current. Now I know initially that in this LED I can apply current up to 100 milliampere. So it may go up to 94, 95 or 96 milliampere because with the passage of time the sources they also improve. So let us start with the value. So at 0 we are getting the power is in the microbar. At 0 input current the power is almost 0. Okay. So if you go to, say, let us take a step of 2. So at 2, this is 4 microbar.
Just 2, not 0.2. 4 microwatt.
So at 4, it is 7 microbar.
4 by 7.
At 6, it is 11 microbar. At 8, it is 14 microbar, 1/4. At 10, it is 17 microbar. Or I can take a step of bigger step because otherwise we have to reach at 100, we have to take 50 reading. I can take a step of, say, let us 5. Okay. So after 10, I will move to 15. So at 15, now it is 24 microbar of power. At 20, 30 microbar. At 25, 36 microbar. At 30, this is 42 microbar. At 35, 48 microbar. At 40, 54 microbar. Forty-five, 59, 50, 64, 55, 68, 60, 73, 65, 78, 70, it is 81, at 75, 86, at 80, it is 89, at 85, 93, '90, 96, So now it is going up to this value only. You could take another reading maybe at 92. Because it is going up to 93 point some value. So at 92 it is 97. So these are the full characteristics for the LED. So now I have current versus power. Okay. Similarly, now you can draw the curve. You can draw the graph between current and the power. Okay. Now we will now see the power current characteristics of the laser. Okay. Similarly, we have to read for the laser. Make the current 0. Now we shift the connection to laser. Okay. So again, we will take the readings. Okay. So initially it is at 0, so 0 microwatt. So now I know here in the case of laser, the maximum current which can be applied is 45. So in this case, it is better to take a step up 2. So this is 2 milliampere of current. At 2 milliampere again 0 value, no change. Four, no change, 0. Or it is on 0 1. 1 microwatt you can take. 6, 1 microwatt. 8, 1 microwatt. This may be the dark value. 10, 1 microwatt. 12, 2 microwatt. 14, 2 microwatt. 16, 2 microwatt. 18, 3 microwatt. 20, 3 microwatt. 22, 4 microwatt. 24, 5 microwatt. 26, 7 microwatt. 28, 9 microwatt. 30, 15 microwatt. 32, 57 microwatt. 34, 163 microwatt. 36, 284 microwatt. 38, 398 microwatt. 40, 527. 42, 644. 44, 771. So it stops here. Okay. Even at 45, it is 831. So now you see the characteristics. You now readings are with you. Now you plot the graph for both the cases and then you can check the type of the curves you get for LED as well as the laser. So if we move, this is how table we have. So we have just given a table for your reference. So as you go from, say, start, this is the case of LED. As you start from, say, 5 milliampere, you have very small power. As you go from 5 in step of 5, at 90 you get only 84 microwatt of power. In present case, how much it is?
Up to 97.
So again, it depends upon your type of cable, whether how much is the connector is clean, all it matters also. So this is the LED curve, and this is the laser guide. So initially, when the current was low, you see the power was very low. So it started increasing at around 30, and after 30, you see there is a huge increase in the optical power. A rapid change. Okay. Now, if you plot this graph, you will try later on, or those who are at their nodal center, I hope you have noted the reading. You can also submit your reports to your local coordinator. So this is how we get. If you put the curve, plot the curve for LED. So you have a bias current and you have a output power. You will see it follows this type of behavior. So in this case, you see it is not exactly linear. So we have to find where the source is linear, where the curve is linear. That is the region of operation. So we have to find what is the region of operation for our device. So if you look at this curve, you will see starting from maybe around this region, from this point, maybe up to 80, it is almost stayed. It is almost stayed in this region. So after this, it is becoming flat. So the region of operation for this device is from 30 to 80 milliamps. So I can operate my LED source anywhere from 30 to 80 milliamps, depending upon my requirement. If I want more power, I can shift to 70 or 80 milliampere. If I want low power, it can be around maybe 30 or 40 or 50 milliampere. So this is the LED characteristics. Similarly, if you plot the laser characteristics, you will get this type of curve. So current versus power. So at the starting, you will get 0. Very small change. And then after this, after 30, you see there is a third increase in the power. So this portion, it will represent the spontaneous emission. Whatever photons are coming, they are because of the spontaneous emission. Once you cross the threshold 30 milliampere, now you see the stimulated emission starts, and now you are getting a large output. So in the stimulated emission, it is a multiplicative process. So you will get large power. So similarly here, you have to find the region of operation, linear region. So you can find what is the threshold current. So now this is a straight line. Now you extrapolate this curve up to the x-axis. You may get maybe around 30 or 29.8 or near that value. So around 30 there is a threshold for laser. So it means minimum you have to apply 30 milliampere of current. After 30, it is a straight line behavior. So your region of operation in this case, it is around maybe from 32 to 44 milliampere. So LED it always operates above the threshold. So this is the comparison difference between a source, a LED and a laser. So whenever we have to use the source, first of all we have to calibrate. Because every time you are not going to draw the curve. So these calibration curves should be available whenever you start your system, you start your communication, you should set at particular value of current and you will get that much power. You should know how much power is applied to the system.
सर थ्योरेटिकल और प्रैक्टिकल के बीच में कितना डिफरेंस आना चाहिए?
भाई क्या आना चाहिए?
जीरो आना चाहिए वैसे तो.
It is uncertainty. You cannot say this much difference will be there. It may vary from person to person. These are random errors. It depends upon sincerity of the observer. But should not be much difference. we are getting that single type of curve. Okay. So these are the curves for this. So these curves are generally available, and one choose the launch power, because whenever you have to maintain a system, you should know how much power is launched, how much power is reaching at the destination. Because at the destination point, you should get sufficient amount of power, because you are using there a photo detector. Photo detector, it has certain minimum sensitivity. So below, if the power is below the sensitive level, it will not work. Your power has to be more than the sensitivity level of the detector. If you are not getting the right kind of signal at the output, you may have to increase the input power. So your system, it always work on the power budget. We always draw the power budget. How much is the input power, how much minimum power is required at the output, and how much power can be consumed by the optical fiber. Okay, or in between, you may have to distribute the signal to some user. How much power can be provided to a user? So all these are required. So power or these LI characteristics are very important for semi-critical. Okay. So similarly, now I can just show you how the signal travel here. So in this setup, we have this source. Now I have provision to modulate this source. I can apply any type of signal at the input. So on this stick, we have a function generator also. So I can switch on this function generator, and I can check what is the type of signal on the oscilloscope. I can check what type of signal we are applying, because I should know what is the input signal. I should get the similar signal at the output. So you see, this is the signal we are using. Okay. So you can go for measurements. You can check the voltage. The voltage. You can go to peak voltage. Okay. Then you can go for time, and we can choose the frequency. Okay. So it means we have applied a signal of peak to voltage 9.2 volt. Because this function generator gives a signal peak to peak voltage of 10 volt. So around 9.2 volt we are getting. The frequency is 1 megahertz. Okay. So at the output, I should get same frequency. Amplitude may change, because it will pass through the fiber. There are certain losses, so amplitude may change. So I can use this signal to modulate this source. Okay, I can choose, let us say, value of say around 40 milliampere. At 40 milliampere, the power is 519 microbar. This is the input level of the signal. To apply the signal, and then I can check the signal at the output. So you see now, if I check it, so this is 1.06 megahertz at 4.16 volt.
Amplitude.
It means there is a loss of around 5 through
9
when it goes. So it is passing through different, how many, this patch cord is involved, 2 connectors are involved. The signal is always attenuated. So we applied 1 megahertz signal, we are getting 1 megahertz signal at the output. In between, so what happens? This signal is loaded over the source, so it is modulated. Now we are getting a modulated output at the output of the laser. This modulated output is given to the photo detector, or basically it is a photo receiver. Detector plus electronics is involved. So it is a photo receiver. So it demodulates the signal and ultimately providing the same RF signal at the output. We can check whether it is through the source or not. If you apply this signal, there is no signal. It is zero. So it means signal is coming through this your device. Okay? It is not that signal was already there. It is there. So this is the one setup we have in this laboratory for experimentation. Our ME student or our PG, our final year student who come for different projects in the area of electronics and communication engineering, they perform these experiments and they learn how to develop the projects. Okay. So this is the one part where we can compare the characteristics of the sources, which are basically your semiconductor laser or dyes, semiconductor material. So now similarly we have another setup here. We can check the. Now in this case I can only draw the PI characteristics, current and light characteristics. Now similarly we have another setup which is available with us. So here I can also find what is the efficiency of my source. Professor Chavda must have told that when you apply some electrical power and at the output we are getting the optical power. How much electrical power is converted to optical power? That is called the external power efficiency of the source. There is internal power efficiency of the source. You must be knowing. We have the internal power efficiency, which is number of photons within the cavity. Then we have the external power efficiency, number of photons which are coming at the output. Because when you couple power, I discussed in one of the lecture, when you couple optimum power output, when you couple power to the at the output mirror, there are always losses. So complete power is not transferred at the output. So we can check here. So here in this setup, we have one laser dye. This is a laser dye. This is same fiber pigtail. So here here you can see this laser source. It has one input analog. I can apply analog signal or I can apply digital signal. Both type of signal can be applied. So we have chosen a signal of 1 mega. Here it is. So
Kilohertz. 1 megahertz.
So we apply some signal, input signal, because we want to test this device under loaded condition. I will get the values without the signal.
मेगाहर्ट्ज में करना है, किलोहर्ट्ज में करना है. ये मेगाहर्ट्ज में.
जी. So now we apply this. If you are interested, I can check the signal for you. So this is a signal. This is a 1 megahertz signal. 1 megahertz. So check the frequency.
1 megahertz.
Okay. Now this signal will be applied to the laser. So we apply analog signal at this point, and we can check the analog signal at the output. No output. On करिए power supply. Because it is not on. नहीं कोई problem है. There is a problem. तब वो ऑप्शन. यह डीसी मैचिंग करना पड़ता है. Okay, so we are getting the signal at the So then we can adjust this signal. So if the problem is there, sometimes it is because of the offset. And now if in the loading condition, you can apply the signal at analog, and then now this here it has the 2 points. So you can show अगर हमारा वो manual है. See, this is the setup which is required for this setup. So we have to use, these are the some jumpers in the kit. So we use analog input, analog buffer, and this analog signal is applied to analog input of the transmitter or laser die. Now it will be modulated. So I will get the modulated output at this point. So I will connect my optical fiber cord at this point, and it will be connected to the power meter. Similarly, I can measure now in order to find the electrical power. What is required? Input current and input voltage. How much voltage is there? So I into V will give me the electrical power, and optical power I have measured with the power meter. So we will connect it according to this. So we will connect 1 ampere meter. So this is our ampere meter. So it is connected at this jumper. This is our signal here. So it will be connected at 1 and 2. 1 and 2. Okay. Similarly, I will do the voltage signal at 1 point at JP2, and this T we will get the voltmeter will be connected. So then now I have provision for measurement of current. I have provision for measurement of voltage. All these are DC values. Now I will connect the power meter. This is an optical power meter which directly measure the optical power. I can measure it in dB or dBm. Normally power is measured in dBm. I can select the wavelength. I can select the wavelength also. It operates at different wavelength. At 850 nanometer, it is at 1310 nanometer, and it is at 1550 nanometer. These are the optical windows: 850, 1310, and 1550. Okay. So this device I know it is at 1310. It is 1310 nanometer. In this case, this laser is working at 850 nanometer. 850 nanometer. So this LED is at 800 nanometer. Okay. So both these are the in the 850 window. This is for 1310. We have another setup where we use the 1550. Both 1310, 1550. So we will connect the other end of this fiber to the meter. There is always a notch, and we have to adjust it. Otherwise, you will not be able to put the connector. So now you see we have the power out. This is the optical power. So in both the cases, you can see this is the voltage in volt, and this is the current 0.2 milliampere. Now this laser is at a drive, so I can change the current now. Just on this kit, I can change the current. So initially we can note the value. It is 0.2 milliampere. If you increase, let us go to some values. See there it will increase. Let us say 0.5 milliampere. Because they are provided with slow variation, so that large current should not be applied to the laser. So let us say 0.4 milliampere. At 0.4 milliampere, how much is the voltage? 0.95. And how much is the power? Minus 58.89 dBm. Okay, dBm. This is very small power. Okay, as you go towards the zero, the power goes on increasing. This is on the negative axis. We are going from negative side to 0. So 0.4. 0.6. Again voltage is 0.98 and current is minus 50. Power power is minus 55.04 dBm. Let us 0.8 milliampere 1 volt, and power is minus 52.52 dBm. So 1 milliampere voltage 1.02 volt, and power is minus 50.85. So 1.2 voltage 1.03 volt, and minus 49.51 is the power. 1.4 voltage 1.04, and power minus 48.65. 1.6 again voltage 1.05, and power is minus 47.92. 1.8 1.06 volt minus 47.05. 2 voltage 1.07, power minus 46.53. 2.2, this is 1.08, and power minus 45.98. 2.4, it is 1.08 minus 45.32. 2.6, 1.09 minus 44.83. 2.8, 1.09 minus 44.47. 3 is 1.10 minus 44.09. 3.2, 1.10 minus 43.73. 3.4, 1.11 minus 43.34. 3.6, 1.11 and minus 43.07. Now I will take bigger step because it will go up to 12 milliampere. It will take long time. I can go to 4, maybe a step up 4. Then we will start the voltage is 1.12. Power is minus 42.225. So 4.4. 1.13 minus 41.56. 4.8. 1.14 minus 40.99. 5. 1.14 minus 40.69. 5.4, 1.11 minus 40.10. 5.8, 1.16 minus 39.52. 6.2, 1.16, 38.84. तो स्टेप ठीक चल रहा है. अर्लियर इट वाज 0.2, नाउ इट इज 0.4. तो आप अकॉर्डिंगली आपको वो पॉइंट मिल जाए. बिकॉज अदरवाइज इट इज डिफिकल्ट टू प्लॉट द ग्राफ. एक सिमेट्रिकल स्टेप होना चाहिए. तो 6.6, it is 1.17 minus 38.12. 7, 1.17 minus 37.75. 7.4, 1.18 minus 36.97. 7.8, 1.19, 36.10. 8.2, 1.2 minus 35.43. 8.6, 1.12 minus 34.06. So at 9, again 1.2 volt minus 28.79. 9.4, 1.20 minus 24.54. 9.8, 1.21 minus 22.25. 10.2, 1.21 minus 20.77. 10.4.
10.6.
10.6, 1.22 minus 19.02. So at 11, 1.22 minus 18.36. 11.4, 1.22 minus 17.58. 11.8, 1.23 minus 16.80. 12. So it is 1.23 minus 15.88. So 12.6, 1.23 minus 15.21. 13. So at 13, 1.23 minus 14.73. This is the maximum current I can apply. So up to 13 milliampere, when you apply 13 milliampere, you get minus 14.54 dBm of power. We started from minus 58, some value around minus 58. So it moves from minus 58 to minus 40. So almost 34 dBm power change is there. 48 to 58. So 44 dBm. So 44 dBm power is change is there. So now you plot the graph. Now you have current, you have voltage, you have power, optical power. So you calculate. You can plot the graph. So but be careful when you plot the graph between the current and power. Your power should be in milliwatt. It is a dBm. You can convert dBm to milliwatt power. Power in dBm is minus 10 log T2 over 1 milliwatt, because we have taken a reference as dBm. So it means your reference power is 1 milliwatt. So use the unit dBm, say 1 dBm equal to minus 10 log base 10 T2 over 1 milliwatt. You convert it, you convert your dBm power into milliwatt power, and you plot the graph, you will get the similar curve as your LE. Because we want a linear graph, linear current, linear power. Your power is, we have noted it is in the log form. So you can calculate at particular value of current. Say when you apply 5 milliampere of current, you have the voltage. You can find how much is the optical power. You know I into B electrical power. You calculate how much is the optical power. And from optical power over electrical power, that will be your external power efficiency. So you can find the light output characteristics of the device, and also you can find how much is the external power efficiency. These are the two parameters for any of the optical source. You should know what is the external power efficiency. So this is how we can study these semiconductor lasers or LEDs. So in case you have any doubt or any query, you are most welcome. कोई इनके बारे में आप पूछ सकते हैं तो जीरो कर दीजिए. मूव करिए थोड़ा सेंटर्स तो मैं बंद कर देता हूँ. Our participants are different nodal centers, Banana University, Gurdaspur. कौन से सेंटर है जी?
Gurdaspur.
Hello.
Hello, good afternoon, ma'am.
Good afternoon, sir.
You could see the demonstration work. It was very
Sir, it was quite clear today. We are already performing all these experiments in our lab. So the session was very interesting also. The people from...
There is some addition to your knowledge?
Sir?
There is any addition to your knowledge? What you are performing here?
Sir, we actually last time the experiments based on the communication kits we are performing, basically digital communication system and analog. Eye diagram analyzer is also Falcon wali kits jo aapke paas thi. Same. Those kits we are using and we are performing the experiment. ये sir OptiSci वाला जो आपका है equipment, ये how much is the cost of that?
Actually, this kit is all from UK. It cost around maybe 5 to 6 lakhs.
So from where did you purchase it? From Germany, I think probably.
No, they have their sole distributor at Delhi. It is Fibronics in Delhi.
Fibronics.
Yeah, they have their Indian representative Fibronics in Delhi. It is at Sant Bihar, New Delhi.
Okay, sir. Otherwise, these experiments we are performing in the lab also.
Okay.
Injection current versus power, but with the help of power meter, we are doing that.
Yeah,
clarity is more in this, and the equipment is more compact otherwise.
It's very good educational kit. You can perform number of ORC experiment on this kit.
Actually, somebody else also told me OptiSci के experiments जो हैं, they kits जो हैं, they are very good.
In case you can have.
I would like to have the address of the same. Could you please mail me that?
You send me the email. You can have contact detail of the representative. Mr. Jaspreet Singh is there from the Fibronic.
Okay. Jaspreet Singh, BPI जो deal कर रहे हैं, BPI software.
8% he is the representative party. He is also dealing with BPI. Yes.
Okay, fine. I know him.
So he has supplied these.
Okay, fine, sir. ठीक है.
Of course, you have to import these. They are come under import.
Okay.
So our second participant at NITTTR University, Gurgaon. NITTTR University, Gurgaon. Your camera is facing the roof of your classroom.
Hello, NITTTR University.
NITTTR University, please align your camera. Good afternoon, Mr. Birla.
Good afternoon, sir.
So, how was the demonstration? You could see? You could see the experiments that we have performed.
Acha.
Hello, good afternoon. This is Dr. Dudeja.
Good afternoon, sir. So, how was the demonstration?
The demonstration was good. I was a little away. These people told me just now that they liked the demonstration. It was very useful to them.
Okay. So I hope the participants they get some knowledge how these semiconductor lasers they are useful, how they can be and how they can be calibrated.
Dr. Chaudhary, I have spoken to my participants. They are 75. There's a big number, and they are all very much enthusiastic, and they were very happy. Except one small thing, that since ours is a large number, the font size on the screen was small, very small for the people sitting at the back. It is only a feedback for the future presentation.
Okay.
Font size should be bigger because we had 75 people
and people at the back could not read what was written on the screen.
Okay.
Otherwise, your entire course has been very, very useful.
Okay, we will take care. We will take care of the font size in the lecture. So thank you very much. Now we will move. Suresh Gyan Bihar University Jaipur. Suresh Gyan Bihar University Jaipur.
Hello.
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 Professor Mitra is there at Suresh Gyan Bihar University.
Yes, sir.
So how was the demonstration?
The demonstration was very good, very explanatory, as well as we are able to download all your PowerPoint presentations, and everybody is very much, I should say, satisfied with the presentations.
The video signal was clear from the lab.
Sir, the audio is somewhat creating problem. Otherwise, the video was very clear.
Okay. Thank you very much. And our center at JEC Jaipur.
Good afternoon, sir. Good afternoon, sir. Good afternoon, sir. Sir, can you hear me?
Yeah, I can hear you. Can you
Yes,
hear?
sir. Sir, your demonstration was very, very nice and knowledgeable, and definitely we will implement in a lab. If we will think any question or queries, definitely we will consider to you, sir.
Okay. You have any question?
No, sir. There is no question.
Okay. Otherwise, if there is any question, you can wait to me and I will reply from the mail.
Yes, sir.
Okay. Thank you all the participants. Now there will be another session that will be in the handed over to talk, and in between we have just 10 minutes tea break, and we will start the lecture at 3:45. So I request Professor Rina Begwilla to ask or ask your speaker and all the participants to start the session at maybe 3:45. Otherwise, it will be very late. And I request all the participants to be there at around to quickly take your tea and come to your classroom at 3:45. So there will be a lecture by Professor Reja from MT University, uh, uh, and we will introduce the topic at 3:45. Okay. So I hope all will be there at 3:45. चलिए क्विकली चाय पीते हैं और 5 मिनट में वापस आ रहे हैं। जमीन का थोड़ा
You know, we have to create that kind of classrooms and in our studios and so on. I would like to set up, in fact, a studio where we are in a position to deliver such lectures live to our class and beam these lectures live to all other Amity University campuses and great many other places. In fact, already you must have seen there is an advertisement in the newspaper where Amity University has started a unique experiment in which the courses are already online, available for.
Hello.
Hello. Hello.
University.
Yes, yes. Are you able to listen me?
Yes, I can listen you, sir. एक आप ना एक स्क्रीन पर ना इंटायर स्क्रीन कर दीजिए। हाँ जी सर, इसको ऐसे रहने दीजिए H8 पर, और जो दूसरी पे आप प्रेजेंटर को अपने आप इसके सामने प्रेजेंटर खड़ा कर दीजिए दूसरी आईडी के सामने।
ठीक है, वो मैं करता हूँ।
E5 वाली आईडी पर इंटायर स्क्रीन हटा दीजिए।
वो मैं कर रहा हूँ जस्ट गिव मी अ मिनट।
क्या करूँगा? अभी लोडेड है, मैंने अभी चेक किया। मैंने चेक की थी, सुबह और इसमें बहुत टाइम हो गया। और द पेज लोडेड द पीपीटी जो मैंने कल भेजी। और देख लीजिए, और 14 लोग हैं, तो अभी देखो कितने लोग। कभी मुझे लगता बाकी जो इतने की होंगे वो दिल्ली वाले तो भागे हुए हैं कभी हैं। So good afternoon, all the participants at different knowledge centers. We are back after tea. I hope all the participants they are there after the tea.
दोनों चीज आ जाएंगी। हाँ सर, दोनों आ जाएंगी। नहीं, एट ए टाइम वहाँ क्या आएगा? वहाँ पे सर दोनों चीजें आएंगी। जब आप वो बोलना चाहेंगे तो आप स्क्रीन मैं मुझे मेरा टाइम सिर्फ 5% चाहिए। मोस्टली स्लाइड्स आएंगे सर। स्लाइड्स अदरवाइज ओनली स्लाइड काम कर रहा है। करो यार, अब दो मेरे को इतनी टेक्नोलॉजी नहीं आती।
सर आप E5 पे अपनी प्रेजेंटेशन खोल लीजिए जिसपे आपने फुल स्क्रीन किया हुआ है।
ओके मैम।
सर इसको स्लाइड शो कर दीजिए F5।
Yeah, sir, that's it. Okay, this is slideshow. It is not there. It is in the slideshow mode.
सर जो इस सिस्टम पे आपने H से लॉगिन किया है, H से उस पे स्क्रीन शेयर बंद कर दीजिए, उस पे कुछ शेयरिंग नहीं करनी।
Okay, sure, I'm doing it out.
सर आपके दोनों सिस्टम पे, सर आप एक ही सिस्टम पे काम कर रहे हैं क्या? दोनों पे नहीं है, एक ही सिस्टम पे 2 आईडी से लॉगिन लग रहा है मुझे तो, पर 2 कॉल स्टार्ट नहीं होती। दो सिस्टम है। सर आप एक सिस्टम पे स्क्रीन शेयर कर दीजिए, एक सिस्टम
पे वेबकैम ऑन रहने दीजिए।
पहले का जो वेबकैम
एक वाला जो ऐसे ही रहने दो, अभी एक ऐसे ही रहने
तो कुछ मत करना।
अभी ठीक हो? आप नहीं हो?
अब आपके इसी सिस्टम का माइक यूज होगा, जो दूसरा सिस्टम है उसके पास ही रखना, और जो दूसरा सिस्टम है ना उसका माइक तो मैं ऑफ कर देती हूँ, स्पीकर भी ऑफ कर दीजिए उस पर, क्योंकि फिर दोनों में साउंड आएगा। तो जिस पे आपने स्लाइड की है उसके स्पीकर्स ऑफ कर दीजिए। जो सुबह वाला सिस्टम है वो आपके एज इट इज है, उससे आपको साउंड आएगा, दूसरे के स्पीकर ऑफ रखना है। ठीक है सर?
अभी is okay now?
Yes, yes.
Yes.
Now
I'm just speaking. Is it okay now?
Yes sir, yes sir. Sir आप
Okay.
Sir.
Yeah, please tell me.
Yes sir, we
can start now.
Yeah, we can hear you.
Yeah, please tell me.
So good evening, all the participants at different order centers. I could see all the participants at different centers. Please occupy your seat. We are going to start the session.
है ना ये चलेगी इसके थ्रू आप बोल रहे हैं जो आप जिससे आपका ट्रांसमिशन आ रहा है
तो मेरी फोटो नहीं आएगी.
फोटो नहीं आएगी सर
फोटो जगह देख लो. इन द बिगिनिंग नहीं आएगी. Beginning, they should know who is speaking. In the first 1 minute.
ये क्या करेगा.
So, Professor Birla, you are ready with the setup?
Yes, sir. We are ready.
Could we start the session?
Yes, sir. We can. Sir, let us introduce to the Dr.
I will introduce.
Yeah. You will introduce, or I get this honor.
You can do if you like, sir. It will be a privilege.
Okay. I have your biodata. I will introduce. So good evening, all the participants. Now we have another session. Now session will be. I'm thankful to Professor Reja. He agreed to share his experiences while working in the area of lasers and optoelectronics. So this session will be by Professor Dr. Jayapal Dudeja, who is professor at MIT University, Gurgaon, currently working as director of MIT Institute of Laser Technology and Optoelectronics at MIT University, in addition to many other research and teaching activities. This institute is mainly running MTech course in laser technology and optoelectronics also. Dr. Dudeja completed his PhD in physics, optoelectronics from IIT Delhi. He has more than 40 years of experience in teaching and research, mainly in laser technology. This includes about 24 years of service as senior scientist in DRDO and also as principal director of an AICT approved engineering institute in Haryana. So after super innovation from DRDO in 2008, he was there. He is founder and chief architect of MTech course in laser and electro-optics at the Institute of Armament Technology, Pune. DRDO in 1989. There is some technical problem. I'm sorry, the system is hanged. Just give us few seconds to correct it. उसकी वजह से तुम्हें वो बंद कर दें। नहीं सर, उनकी शायद उनका सिस्टम है। ठीक है
सर 1 मिनट अभी वो कर रहे हैं रीलोड।
यही क्या नहीं बैठ जाएगा। अरे सेंटर आर कनेक्टेड, सिर्फ उन्हीं की प्रॉब्लम है।
यस सर,
कोई बात नहीं, उनको तो वो तो जानते हैं सभी उनको।
लेक्चर तो सर उन्होंने ही देना है।
अच्छा
ये सर आप कनेक्ट कर दीजिए। ठीक है चलो अब जल्दी सॉर्ट आउट कर दीजिए। यहाँ पर भी देखिए उनकी
नेटवर्क तो
सर उनकी नेटवर्क प्रॉब्लम है अभी। सर वो सॉर्ट आउट कर रहे हैं 2-3 मिनट कह रहे हैं लगेंगे अभी।
ये परशुराम सर टाइम पास करके तो बात नहीं हम लोग तो बातें कर सकते हैं ना।
हाँ जी सर।
हेलो
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 हेलो हेलो यस सर।
हेलो
हेलो यस
यस सर
sir your system is ready now.
sir actually we just got the last minute IT technical fault.
Sorry sir.
Sir we just got the last minute IT technical fault. Is it okay?
ओके सर आपको एक सिस्टम के माइक रखिए या दूसरे की बंद कर दीजिए। कुछ इको हो रही है।
Dr. Chaudhary, are you
हेलो सर आप एक दोनों सिस्टम में से एक के स्पीकर्स ऑफ कर दीजिए प्लीज।
हाँ कर रहे बंद कर दिए। इसमें स्पीकर से hello
हेलो यस सर।
am I audible to you?
Yes sir you are audible.
Sir are you audible?
सर आपके दोनों स्पीकर ऑन है इसलिए इको आ रही है। यहाँ पर एक स्पीकर बंद कर दीजिए।
Is it okay now?
Yes sir now it's okay.
इसको बंद कर दो अगर वहाँ प्रॉब्लम कर रहा है।
Yes sir now it's okay sir.
इस वाले को बता देते हैं। इसको बंद इसको म्यूट कर दो। इस वाले पे लगा दो। सर केवल आपकी साइड से लेके प्रॉब्लम। हाँ कोई नहीं बाय। केवल साइड है ठीक है। मेरी शक्ल इतनी अच्छी नहीं है। इसका स्पीकर बंद करना।
इन्हीं के सिस्टम की प्रॉब्लम है।
Yes.
Hello.
Hello. Hello.
Hello.
Hello.
Yeah, hello. Are you able to listen us?
Yes, sir. I can hear you, sir.
Okay, thank you.
हेलो सर, बहुत डिस्टरबेंस आ रही है अभी आपकी साइड से।
वहाँ से वहाँ लोडेड उसी पे चलाओ, इसको बंद कर, सब दोनों चलेंगे।
हेलो
हेलो
Hello.
Yes, sir. Now
Can you
it's
hear
okay.
me, sir?
Yes, sir.
Can
Now
you hear
it's
me?
okay. Yes, sir. I can hear you.
Yeah, okay. This is Dr. Dudeja. There was some technical problem in the connectivity, and now it is restored. And all the people have already seen my face. Now you may not be able to see my face. He says it's okay. So I will manage with the slides only. Will that do?
Yeah, it's okay now. You can start, sir.
मैंने कहा मेरी शक्ल नहीं दिखाई दी, कोई शक्ल दिखाई दे रही
नहीं सर, वो तो दिख रही है।
जी जी
Sir, we can see you and also see your slides, sir.
Okay, that's fine. Now you can see my slide. This slide, the MET is written on the logo on the first one. Can you see that?
Yes, sir.
Okay, fine. That's fair enough. So good afternoon, everybody at various places. I am Dr. Dudeja. I am Director of MET Institute of Laser Technology and Optoelectronics at MET University, Gurgaon. Okay, now I am going to speak to you on in the last 2 days. I see that Dr. Chaudhary and team, now you have switched on to the applications of lasers mode. So my presentation is also going to be on the applications only. And on the first day, when the participants were asking me what are the applications of lasers, I said in 1960, when for the first time Dr. T.H. Mayman in a press conference was demonstrating the action of the ruby laser, and his team was also there, including lab workers. So the press people who were also knowledgeable technically, they were asking, can your laser work in communication? The answer was yes. Can your laser work in spectroscopy? The answer was yes. Can it treat the patients? Answer was yes. So all these answers, when the yes was coming, so one of the lab assistants, he said, laser is a solution, looking for a problem. Okay, so you can have thousands and thousands of applications of lasers for better precision, for solutions which no other device, no other tool can find. In military parley, I have been in the defense for more than 3 decades, so they say better kill probability, and so on. So I am going to touch upon only one applications, this being the penultimate day, just one of the applications in which I have worked extensively in the DRDO. And that application is going to come on your screen.
This is laser-based standoff detection of explosive materials, and my name is written there. I am Professor Dudeja, Director, MIT University, Gurgaon. Now, once again, for the last time, I am asking, my slides are clear to you, everybody? Anybody should say that you are able to see the slides properly?
Yes, sir, we can able to see your slides.
Oh, thank you very much. Thank you very much. I hope we will have a wonderful time together.
Yes, sir.
Yeah. So this is a scene from the Mumbai train blast. Some of you may remember that several years ago there was a bomb blast in the Mumbai train, and this is the devastation caused. A dead body or an injured fellow is being carried by some people. Now, this is the blast effect of an explosive planted in a vehicle. Now, this was a photograph taken from a damage caused by an explosives by terrorists in Delhi. Sir, if you remember, one of our person, I will not name him publicly, his family lost this thing. So this is that blast. So what is the threat? This is the major threat being faced by the world these days. One of the most common forms of terrorism is the use of explosives that has cost the lives of a large number of people in different parts of the world. So this threat is not specific to India. India, it is too much. In many countries like Iraq and other countries is also there. But this is a problem being faced by the world all over. Hardly a day goes by without a suicide bomber's attack or a car bomb or planting of explosives at a public place, etc. A low-budget terrorist can make deadly explosives from commonly available materials and amplify the killing power of his or her bomb with nails, nuts, and bolts. They say explosives are the poor man's bomb. If they are terrorists, they have to spend very, very little to create devastation. Suicide bombers who penetrate crowded public places typically wear bombs that are easy for them to trigger. We have to develop. So what, as laser people, what is our role? We have to develop methods to detect these explosives at their, this is underlined, pre-detonation stage, before they are exploded. So this is in the timeline. I have shown this. So at this, see, when the attack is planned, at this stage itself, we have to detect this explosive at the pre-detonation stage. Afterwards, the action takes place the other. But we are concentrating on the first part, at the pre-detonation stage. Now, what is the reliability of any explosive detection system? The lives of the targeted people depend on the reliability of the explosive detection systems. For a detection system to be reliable, it must prove to have a very high probability of detecting explosives if they are present. There should be practically nil false negative alarms. What do you mean by negative alarm? Negative alarm means the explosive the material is present, but your sensor is not able to find out somehow. That's a very dangerous situation. We cannot afford this. Ideally speaking, we should have a zero false negative alarm, and then very few false positive alarms. What do you mean by positive alarms? That means the explosive material is not there, but still your sensor is finding. Of course, redundancy is okay, but not that every time the explosive is not there and you are finding. It is like some shepherd went to the jungle, sher aaya, and the villagers used to wake up and run towards his rescue. He was telling a lie. But one day when the actual sher came, so nobody came. So the false positive alarms also should be very few, but I am repeating, the negative alarms should be practically zero. That means when the explosive material is there, so you should be able to detect 100%. So Now next is, which are the commonly used explosives by the terrorists? I am not going to read out the whole list. RDX, PETN, TNT, DNT, etc. You see in the yellow color, I have written nitro, nitron, nitro. That means it is the nitrogen content, which will be for each of the explosive material. It is the nitrous compound, nitric content, which will be spectroscopically determined, and each one will have a spectral signature. Except these two, TATP, triacetone triperoxide, and HMTD, which are not having the nitrogen. So we will have some other material, some other method which will not be focusing on the nitrogen detection. But almost all, other than these two, almost all the explosive materials are having nitrogen as N as the component or in these compounds. Now these are the standard explosive materials, TNT, RDX, etc. But mind you, nobody uses pure and standard materials. They are either improvised or they are contained in the plastic containers. For example, improvised, which is most of the time it is done, ANFO, it is a very popular is a wrong word as far as the peace-loving people are concerned, but popular amongst terrorists. This is ANFO, ammonium nitrate plus fuel oil. Then urea nitrate, TATP, as I have said earlier, triacetone triperoxide. So these, for example, if you see these days, ammonium nitrate, you cannot buy it from the shop. This is banned because terrorists are misusing it. Similarly, the explosive materials can be sealed in plastic containers. Now, I was talking about TATP once again. I will emphasize TATP is the hot favorite explosive of the modern day terrorists. It is one of the most sensitive explosives, susceptible to impact, temperature change and friction. Little bit, there is a jerk and it explodes. Even these terrorists who are highly indoctrinated people, they are not afraid. So it is very, very easily detonated. TATP can be prepared using commercially available materials like acetone, which is a nail polish remover, commonly available, and hydrogen peroxide, a bleaching and cleaning agent, and sulfuric acid. These three things can be taken, and people have done it in the past, but they were caught. These three things were taken separately. That is why now in the airports liquids are not allowed. Okay, even your liquid, this shaving lotion is also people are objecting. So these three things are were taken together, and in the washroom, etc., they were being joined to make explosives. TATP has been used by many suicide bombers, including the shoe bomber, which is I am showing this photograph in the next page. Can you see this? This is that shoe bomber. See several names: Richard Wright, Raja, and so on. He was arrested on December 22, 2001 for attempting to blow up, although unsuccessfully, the American Airlines flight 63 from Paris to ignite explosives hidden in his shoes. That is why he is called shoe bomber. Now these days people are telling you to remove your shoes at the airport, so they check everything. Now the title of my talk is and was standoff detection of explosive. I didn't say remote detection. So what is the difference between remote detection and standoff detection? In remote detection, without reading the slide, I can tell you remote detection means the people, those who are operating that device, they are at a safe distance, but they send the device like a robo to the that area where the explosive material is there. So this was one of the ideas in the DRDO, that those terrorists infested, those Naxalites, you send the robo to jungle. Then somebody laughed. The robo they will send back. What is this nonsense you are talking about? Okay. So standoff detection, where your detecting device as well as the personnel operating that, both are at a far off distance, at a safe distance, and doing this job. And it is the laser which can do the remote detection. No other device, no other tool can do this standoff detection of tens of meters, and sometimes up to 2 to 3 kilometers. Now, what is the expectation from this detection system? There should be a near real-time detection of traces of explosives. Mind you, at parts per billion and parts per trillion. You know, the fellow is hiding the explosive material in the shoe, or hiding somewhere. So that some plume, some vapors will be coming, and from a distance you are trying to spectrally detect that. So it will be parts per very little. So your laser has to be powerful enough, and the line width, the wavelength has to be sharp enough to detect that thing spectrally. So, and another requirement is that these explosive materials, they are not only concealed, that is the challenge, but are placed in the plastic containers. We have to detect them in ambient conditions, in situ, there and then, without making any changes, without the requirement of collection or preparation of the sample, with practically, as I told you, the difference between nil false negative alarm and false positive alarm, with practically nil false positive alarm means if it is there, you cannot afford to ignore it. It has to be detected. The sensor and very few false positive alarm, and up to a standoff distances of tens of meters. So there are several laser-based techniques. I will be talking only 3 of them in the limited time. So these 3 are the most prominent these days world over. The first one is LIBS. LIBS means laser-induced breakdown spectroscopy. This is a typical equipment. Typically they use ND-YAG laser. So this is focused onto the sample. It could be straight, it could be folded, depending upon its location, and then it focuses onto the sample, and sample, part of it, microgram to nanogram sample is only, the breakdown takes place. So the quantity is so small, there is no harm done, right? But you are creating the vapors which you can detect. And then there is a delay generator. Why there is a delay generator? Next slide will be clear. And then you are getting the spectral signatures of this and identifying that particular explosive. Now let us understand once again what is LIBS, laser-induced breakdown spectroscopy. LIBS is a detection method that uses a laser with high energy enough to break down the sample into plasma. LIBS operates by using the laser onto a small area at the surface of the specimen. When laser is discharged, it ablates a very small amount of material in the range of, as I said, 1 microgram, even few nanograms sometimes, which instantaneously superheats, generating a plasma plume with temperatures of about 10,000 degree Kelvin. At those temperatures, the ablated material dissociates or breaks down into excited ionic and atomic species. During this time, this plasma emits a continuum radiation which is of no use, which does not contain any useful information. So you have to allow that plasma to cool down so that you get your spectral signatures. That is the next slide. Within a very small time, the plasma expands and at supersonic velocities and cools. At this time, the characteristic atomic emission lines of the elements can be observed. So you see that you have to have a delay, you have to have patience. The delay between the emission and continuum radiation and a characteristic radiation is of the order of 10 to 100 microseconds, okay, depending upon the material. That is why it is necessary to temporarily gate the detector, that time delay, as I was telling. Okay, now you see this is the laser pulse has gone, then there is a continuum, and after some time only you can get the spectral signatures. Now LIBS is a very sensitive technique requiring as little as a few nanograms of some samples, micrograms to nanograms. LIBS spectra of several explosive compounds have been the other day I was reading in the some technical magazine. So they found a painting. First they cleaned it with low power laser, and they found it could be probably hundreds and maybe thousand or more than 1,000-year old, and what a beautiful painting. So they used Lips technique. Only a few nanograms of this was used, and they saw what is the painting material they have used that it can survive for such a long time. Online industrial, when you are mixing material online, you can see how much is the ratio of each material through Lips technique. Okay, so other than defense, there are many applications of Lips. Lips spectra of several explosive compounds have been reported by many workers in the world. Stand-off Lips could be utilized with proper telescope focusing and collection optics. This telescope focusing, you need special equipment. Your material could be 100 meters away, it could be 50 meters away, it could be 75 meters away. So every time you will not, adjust the focusing. So there are variable focusing telescopes are available, which are fitted to the Lips detection equipment. Some researchers have used Lips to detect suspicious powder at hundreds of meters away. This is the diagram which I am showing, telling the importance of the digital delay generator. Now this is a system which has been made by Applied Photonics, which has materials more than 60 meters. Advantages of this technique: Lips is a very sensitive technique with high spatial resolution, that means very small focal spot. Many types of materials can be investigated, including solids, liquids, and gases. Vaporization and excitation of the sample occurs in one step, instantaneously. In majority of the cases, no sample preparation is needed in situ. Lips provides an online and real-time analysis of the Lips sample, requiring no contact with the sample. Stand-off Lips could be utilized with proper telescope focusing, as I was telling earlier. Limitations. Each technique, what I will be doing is that I will be talking about 3 techniques, and each technique has got its advantages as well as limitations. That means no single technique should be used and with 100% reliability. So this is the last slide on Lips. There are limitations of this. In a real environment, there will be many interfering subsystems, surrounding things. There can also be contribution from the nitrogen and oxygen in the air. Another problem is the peak intensity variations. And then another one is, suppose there is a cargo which has come, let us say, through sea route, and in the container there is an explosive, and you are focusing it on, maybe you are scanning in a given time. There could be some spot which may be missed. So you are not able to, in that particular portion, the explosive material may be hidden. So these are some of the limitations. Besides these limitations, Lips is the most popular technique going on in the world. Now I am coming to the next technique, that is LIF, laser-induced fluorescence. Laser-induced fluorescence, as you already know, this is the laser light. It is some broadband material of that material. So the very narrow incident light need not be there. Any one of these lines can absorb it, and then there is a re-emission after some time, after the fluorescence time, and then finally it goes to the ground stroke. It is this line which gives the spectral signatures of that NO2 or TATP hydrogen peroxide. Okay, so it is this line which is there. So, but there are some limitations of this kind of a technique because the broad breadth of this thing. So LIF spectra, laser-induced fluorescence spectra, have no characteristic individual bands, and the information is distributed over a wide spectral band. And then, there are so many other molecules like nitrogen. See, it's nitrogen-based, mostly nitrogen-based detection. So there is a nitrogen in the air, NO2, NO, everything is there. So there will be confusion about this. And another thing is that there can be quenching of the fluorescence. That means reabsorption by other molecules. So they has got some limitations. So people have improvised on this, the laser-induced fluorescence itself. Now you have pulse fragmentation followed by laser-induced fluorescence. What does it mean? that this first you fragment with the help of the laser, you do the fragmentation, and now as you go, I will talk to you side by side. This detection concept is based on a single laser beam inducing a tandem process.
Hello, sir.
Yeah.
Sir, can you
Yes,
put that notification on your slide?
Pardon? Pardon? Yes, you want to say something?
Okay, sir. Now fine, sir. Fine, sir.
It's okay?
Yes, sir. Yes.
I will be finishing it in less than half an hour. Is it okay?
Yes, sir. Yes.
Less than half an hour. I am already to the second technique. Third is the Raman, our great C.V. Raman, and then it will be last slide after that. Is that fine?
That's fine.
Yeah. So this pulse fragmentation and laser induced fluorescence combined, I will go to the next slide, this one. Okay, the first of laser is able to dissociate all these compounds into NO. Then NO goes excited from this place to this place. And the beauty of this is that it goes from this zero state to zero state, but when it re-emits at a larger frequency, So, which is the characteristic thing, that means even if there is some small component of NO in the atmosphere, it does not interfere with this. So then you can get it. That means if you are having a 248 nanometer UV laser, what you get is 225 to 240 nanometer at a shorter. It is equivalent to anti-Stokes radiation kind of equivalent of that. That means at a higher frequency. So that means this technique is more reliable than ordinary laser-induced fluorescence. So these are some spectra which people have obtained with the help of this. And the last technique, out of several techniques, I have already enumerated 3. This is resonant Raman scattering. This is our great Dr. C.V. Raman. We are proud of this man in our country. So many of you know what is Raman scattering. There is an incident laser beam, or then this is a virtual or actual level. Then you come to, this is a Stokes frequency. Anti-Stokes is enhanced frequency. Stokes is the shorter frequency. So depending upon the characteristic of which molecule you are studying, so the difference between this frequency and this frequency is the difference between this. So this way you find out the signature of that particular molecule. Okay, but the problem with the Raman scattering is the return signal is very, very weak because it is virtual level. So if instead of virtual level, if you can get an actual level, then it becomes a resonant Raman scattering. So that time the return intensity is enhanced several times. So that is the resonant Raman scattering. Okay. Now laser-induced fluorescence was also a similar diagram. Raman scattering is also a similar diagram. What is the difference between the two? See, without even going through the slide, I can tell you that in the case of the resonant, the laser-induced fluorescence, this particular wavelength will be same as long as it is absorbed by any of these lines. This wavelength will be same, though line width will be very large. So that is, in the case of resonant Raman scattering, this will always be different. It will be equal to the difference between the difference between this h nu minus h nu dash, and that is this difference. So that is the difference between resonant Raman scattering and laser-induced fluorescence. In any case, laser-induced in the time scale, Raman scattering is almost instantaneous. So whatever comes immediately is resonant Raman scattering. Fluorescence will come after some time. So if you observe the spectra in the time scale, so you will be able to distinguish between RRS, that is resonant Raman scattering, and the laser-induced fluorescence. These are the spectral signatures, are TNT and other this thing. So that the last, I think only couple of slides are left, so that people with diversified background can follow this. Therefore, deliberately I have not made it very involved presentation so that majority of you should be able to follow. Hybrid sensors means a combination of this. This is a typical diagram. That means in the time I have just gone to the next slide. The diagram means, as you can see, conclusion means I am already on the last slide. What was the diagram? That means on the time scale, first you find the Raman scattering, then after a certain time, then you find fluorescent spectra, and then you focus that beam and ablate it, and you will get a Libbs technique. So you can get all three. So for example, the thumb rule is if 2 out of 3 techniques are giving you some indication, then you should be more sure than a single technique. So the world has come to the hybridization, more than integral sensors, hybrid sensors. That is so that the false negative alarms reduce to practically zero, and false positive alarms, they are very, very few. Okay, that is the thing which I want to do. In fact, this talk was presented by me in one of the international conferences in University of Miami. Based on that, I made it simple and presented it to you. Now the conclusion slide. There is no single technique suitable for the standoff detection of all types of explosives in different scenario with 100% reliability. That is the underlying thing. A hybrid system, that means integrated sensor employing combination of these techniques, would system. Finally, there is always going to be, yeah, this is very dangerous statement, last statement of this presentation. Finally, there is always going to be a race in the adoption of newer technologies by the modern age terrorists, aided by vested interests. These vested interests, their salary is far higher than the scientists who are poor fellows who are making this thing. So there will always be countermeasures. Whenever there is a technique, they will find something. They will mix something in such a way that they will, these signatures will be blocked, and the intensity will be there. So this thing has to be. So there is a continuous race between the peace-loving scientists and the peace-loving citizens and these terrorists. So with this, this has to be kept in mind. Thank you for your kind attention, everybody, including Dr. Chaudhary sir. You gave me this chance. I am grateful to you. MIT University is grateful to you, and thank you to all the centers. I hope you will give us opportunity in future also. Any questions, please?
Reja, in fact, this was
yes, sir.
In fact, this was a new area of detection of explosive materials, which I could not add to my presentations. So you find during the presentation,
so I have filled the gap.
you have filled the gap, and also you have introduced many techniques, scientific techniques, which are all based on the lasers. Yes. It is not only that there are applications. There are many techniques in research where the lasers are finding very important tool in those areas. So
yeah, in my earlier presentation, I have listed about 1 dozen techniques. Okay. So if there is a chance in future, I will, and I am giving little more time, I will list out all those laser-based techniques, which are about a dozen.
Yeah, in future definitely we will get benefit of your expertise in this area. So this is the, you see here in all these techniques, it is the laser which is bringing all the solutions. So as mentioned by Professor Dureja, laser is a solution to any of the problems. You name the problem, you will find solution with the laser. So I once again I am thankful to Professor Dureja for giving a very interesting talk or very important information. Where now many of our detection agencies now they are using lasers also. So now I invite the question from
Dr. Chaudhary, with your permission, I want to ask to anyone in any one of the 7 center sitting, particularly those people who are non-laser people, could you follow some of my slides? I'm asking somebody, anybody can answer this question.
He's
Because
asking.
then I will think my effort was useful.
Definitely, our participants at my center, they are very happy. They could follow and they find it's very useful, and it added a new dimension to their knowledge.
Thank you very much. I'm delighted. A teacher gets satisfaction by listening to these things.
Definitely, it was very interesting.
Thank you very much, sir.
Participant at Guru Nanak Dev University, Gurdaspur. Dr. Anu Sital, how was that?
Hello.
Yes, hello.
So it was wonderful presentation, and this sector actually we were also not very aware that lasers could be used like this in these type of applications. Otherwise, we have gone through many kind of sensor applications of lasers, but this presentation was certainly beneficial.
I'm happy to hear.
And interesting also, sir.
Thank you very much, ma'am.
In fact, it was also new area for me. So
call me at Chandigarh. I will do the remote delay over there on many other topics on lasers.
Definitely, sir. I will invite you in my next TV program. I will definitely contact you. Our centers are Jaipur, Shreyas Gyan Vidyat University.
Okay. Yeah, I'm waiting for the other questions.
Much different from the other sessions.
Yeah.
And it was very illustrative, sir.
You have any query? Professor Mitra, you have any query? You want to any question from Professor Dureja?
Yes, sir.
No, sir, we don't have any query. It was very explanatory. Slides were very clear.
Okay, so it was self-explanatory. So thank you, Professor Dureja, once again, and thank you.
Thank you very much. I take permission from you to leave this platform, and thank you very much. It was Dr. Chaudhary. You are a wonderful person. People are very happy with you, and you emit very good, peaceful, spiritual vibrations also. Thank you very much. God bless you.
Thank you, sir, for your nice word. Now I'm thankful to also Professor Vivek who arranged this session, and also he has helped. He has also arranged one speaker for tomorrow also. Now with all the thanks, I'm once again thankful to all the participants, and once again speaker for this session. And tomorrow we will again continue with our session from our main studio, and then in the afternoon we have another session and validation session. Okay, so